I'm Bernhard. I'm going to conduct the morning lecture with you today, the whole day. During the rest of the week, you will see other faces of our team, notably Stefan Hageberg here on the front row, who's going to teach on Wednesday and partly on Friday. And in the very back, just before he leaves, that's Sebastian Pons, who was the original creator of this course. We owe him a great deal for setting up the entire thing, creating the initial slide deck and getting us all going. So thanks very much and see you around. Okay. No worries. Thanks a lot. Good. Can everybody on Zoom hear me?
That's a good point. I think they can hear us, but I don't think we can hear them. So you might have to increase the volume on the knob.
The volume here.
Sorry, I forgot one more thing. I broadcast in a moment a link on the Zoom chat for the attendance list, but there's also a piece of paper where you can just put down the name. Any of those will work.
So can somebody on Zoom just say hello to us so we know that you can ask questions?
Hello.
Hello. Yeah, thank you.
Perfect.
Hello.
Okay, great. I think then we're all set and we can start. So, yes. So for this week, we're going to present to you some stuff on C++. This is the Essentials course, so we try to start with some of the basics. This course is intended for people that already have a bit of understanding about programming. And maybe during the first few hours, some people might be a bit bored. We're trying to get everybody on the same page. But like during the next days, we will speed up with like the complexity of the course and it will grow. And if you're still bored at the end of the week, it's not like Stefan said, if you're still interested in C++. No, of course we're interested in C++. We have more advanced courses following up on this one. But today we will start with the basics. And just a couple of words before the course. This course is not for absolute beginners. It's also not for absolute experts. It's kind of hard to judge the audience because everybody comes with their own kind of previous experience they had before. So please also ask questions in between. So if there's something that's just completely out of place, you have no clue what's going on the slide, please raise your hands. Also in Zoom, you can raise your hands. I might not see the hands on Zoom, so you can also try to speak up, or maybe Stefan Hageberg, who's watching Zoom in the audience, can bring that to my attention. Also importantly, for the people on Zoom, we have a Mattermost channel. Please post questions there. If you want to write down your questions somewhere, please post it to the Mattermost chat, because those will be persistent and they stay still after we close the Zoom session. This course is far not complete at all because it's written here on the side, it would take 3 weeks. I don't agree with that. I think it would take 3 months or so. C++ is a really huge language, so we're going to present a selection of what's in there. There's always more. There's much more. We see the course as like adaptive. We try to pick the stuff that we think is important for you. Let's make it interactive. Please ask questions. And we also spend a lot of time looking like at real code pieces. And we also have the afternoon lectures where you're going to try out most of the stuff that we present during the morning lectures. All of the source code for like the slide deck, the afternoon exercises, and like some auxiliary material is on GitHub. We put a link there. It's in the HSF training C++ course. There you can find all the stuff. And there's a download link where you can always get the full PDF of the course slides. Those are also linked on the Indico page. So if you scroll to the bottom of the Indico page, you will also find a link to the slide deck there. And as Stefan already said, we have a couple more courses that you can try out, for example, on the Unix shell, on Python, on version control, and there are also other courses from the CERN Training Center. So there's a lot for you to learn and like programs that you can try and check out. Okay, here's the outline for today. I will start with history and goals of the C++ language and with the language basics. That's what I will cover today. On Wednesday, Stefan Hageberg will do most of object orientation with you. So that's all the part of C++ that involves classes, polymorphism, virtual functions, and so forth. And on Friday, we'll finish off with core modern C++. And we got a handful of tools that we'd also like to present to you. And I think we pegged that partially on Wednesday and partially on Friday. I'm not entirely sure. Stefan, you know? I think we pegged most of them on Wednesday. Yes, that's also an important point. The course is a bit dynamic. We constantly add content, so it's quite hard to judge how long everything will take. So it might be that some content might flow over to a different day or so. So we just see how that goes. That's the content in more detail. And as I said, we'll start with the first column. That's the content for today. Yeah, any questions so far on the organizational stuff, Mattermost, Zoom, afternoon lectures? I think the list with the room assignment is going through. Okay, so then let's dive in. History and goals. The C++ language is fairly old. And it also has a long history on influences. And one of the most notable influences was the C programming language, which was co-invented by Dennis Ritchie together with a couple of other really nice people at the Bell Labs. And that already got influenced by a couple other languages. And the inventor of C++, who's Bjarne Stroustrup, took inspiration from the C programming language. But Bjarne also had previous experience in Simula, which brought a lot of concepts on, for example, classes and object orientation. So those came from Simula. And Stroustrup created a language that was based on C because C was very successful in the Unix environment. But he wanted to bring in the classes that Stroustrup know from Simula. And he created like the first version of C++, and that was called C with classes at the Bell Labs. And that eventually grew and grew into the early C++ and eventually became what is known as ARM C++. And that has nothing to do with the processor architecture, with the ARM architecture, because ARM here stands for the Annotated Reference Manual. And that is like the first version of C++ that had a specification that expressed how the language is supposed to work, how the grammar is defined, what the semantic of the language is. But this was not enough because many companies started implementing C++ compilers and they diverged, and we had different kinds of versions of C++ that were incompatible within each other. So eventually, Stroustrup went for standardization. And in 1998, we got the first version of C++ that was formally standardized as an ISO standard. And that is C++ 98. And since then, we got lots more revisions of C++. And notably, there was a big gap between 1998 and 2011. And that's when lots of other languages were invented. Java came along, C# came along. And there are like reasons for that, why C++ had its kind of niche and why it became important again in 2011. But I don't bore you with all these details. But since C++ 11, C++ ships a new standard every 3 years. So today, we are actually around C++ 23. And let me think what I want to tell you, because I like to gossip a lot. So I need to focus that I don't tell you too much of the history that you might not be interested. Fact is, C++ 20 is like the current official standard. And C++ 23 is a standard that's like currently in the final stage. So we expect it to come out this year. And then that will be like the most recent version of C++. In the meantime, also the C language developed a bit. So also they're trying to have a bit of an evolution. But today we just focus on the C++ part. Yes, we'll discuss up to C++ 20. I think we have just a very few pieces of C++ 23 in there because the spec is like finalized at the moment already. But we'll mostly focus up until C++ 20. Okay, already mentioned C++ 23 is complete. They're currently waiting for like the ISO ballot to actually have it published. Work on C++ 26 has begun already. And every standard brings in a lot of cool stuff. So that also makes, like, if you're into C++ like me, it makes it really interesting to just see how everything evolves and keeps going and so forth. So how do you actually use then like those C++ features and so forth? Many compilers, and you will probably mostly work with the compilers GCC and Clang, which are like the traditional compilers on Linux or Unix systems, and I think also macOS. They have a flag that's called -std equal, and then you can set the C++ version there. For example, -std C++17, and then the compiler is put into that language mode of C++17, and you should have all the features of that language available. And if you want to have like recent features, like for example, C++20, you also need obviously a recent compiler, and we put a table here of what kind of compiler versions you should have. For the afternoon exercises, we will also check your setup together, whether like the PC, the machine, the notebook that you bring with you has a sufficient enough version of the compiler so that we can run the exercises. So that the mentors in the afternoon will check this with you. Okay, why do we use C++? It's a fairly complicated language, so what does it give us? And one of the very big benefits of C++ is that it is adapted to really big projects. And that is due to a couple of features. It's statically typed and it's strongly typed. So this means that when we have source code, we describe the data types that the variable has. And those data types, they carry strong semantics. And this way we can build very large projects, but like make them like compatible, like the different parts really work nicely with each other because we can specify very precisely what certain constructs in code means. C++ supports object-oriented programming, which is one mean to fight complexity. So when software projects become really large, it's important that we can encapsulate pieces of the software, make them only accessible through like a small interface or so that not everybody can reach out to every other piece of the software. And object-oriented programming is one way to do this, and that helps us fight the complexity of large projects. C++ is also still widely used. It used to be widely taught. It gets less and less, which is why it's very important that we have these courses, so we can like still teach the next programmers generation. And also C++ has really many available libraries. So if you're looking for like something that implements like statistical functions, if you look like for domain-specific libraries that can implement certain tasks, there's just lots of stuff available in C++. And that also makes it a good language of choice. C++ is a fast language. It's compiled, unlike other languages like Python. Java and C# are technically compiled, but they're compiled to a virtual machine. But C++ is compiled to the real native processor architecture that you want to run your program on. And that makes it really fast. And it also allows you, in your source code, to go down to the hardware specifics if you need those. And that allows you, specifically in certain places, to express your code for the specific architecture you're compiling for and make it really fast there. That has a couple drawbacks. We get one of the most powerful languages, but that also means it's one of the most complicated ones. And it might also be one of the most error-prone ones. Like people talk a lot about C++ complexity and the weird errors they get and so forth. I leave this up to you to judge how complicated you think the language is and whether the trade-off is worth it. Okay, any questions so far on like the history of the language and what it tries to achieve? Okay, there's one question in the back. We have microphones in the room, by the way, so we'll hand the microphones to the people in the audience. So
it's mostly so the more participants hear what you're asking.
I was just wondering on the C++ origins, does that mean that the base of C has been C99 since 1998?
So that's here. So also the C language kept evolving. And because the C language was such a strong base for C++, the C++ committee tries hard to make it compatible also with the evolution of C. So if the C language introduces new constructs, the committee in C++ often tries to rebase the stuff on the newer version of C so that the languages stay as much compatible as possible. That's the intention here, yeah. Also notice that sometimes stuff gets back from C++ to C. For example, the memory and multi-threading model that C++ developed was later adopted by C, for example. So there's still like a strong cross-influence between the languages. Any other questions? Good. Then let's dive into the language basics. And we start with core syntax and the basic fundamental types. And that is, I think, the first piece of C++ code that we have on the slide. And it should just give you an overview of how the language looks like. And most of you will be familiar with some of the things, like we have here, for example, preprocessor directives. We include another header. That's how we put in, like, pull in pieces of code from other people or from the standard library. C++ has comments, like the one on line 3 here, and that from line 4 to 6 is a function. Functions have a name and arguments, return types, and then there is like implementation inside the functions. Like here, for example, std out hello world I that prints to our console the string hello world, and then an integer variable that is called I here. Then we have the main function, and main is the entry point into the program. So every program, when it starts up, when the operating system launches the program, it will start execution at the main function. So this is where everything starts in your program. And you have variables here, and there are control structures like the for loop, for example, that loops a couple times, and so forth. We look into all of those pieces individually now, and check out the detailed semantics. And the first thing we talk about is comments. In C++, there are two styles of comments. The first one on the top, it starts with 2 forward slashes, and that is called a line comment. And it's called that way because it starts at the 2 forward slashes and then extends until the end of the line. So when there's like the new line character that breaks the line, that's where the comment stops. So there's no need to explicitly terminate the comment here. Then there's a different style of comment, which is the multi-line comment, and that starts with a forward slash and then an asterisk. And that comment goes until there is an asterisk and a forward slash again that closes the comment. You can have arbitrary like characters in between. You can also include asterisk in between here, like the one on line 5. That is not necessary for the comment, but some people like to do that because it looks good or may have certain aesthetics. But what's important is like the forward slash asterisk to start and the asterisk forward slash to stop the comment. And this also allows us to put the comment in between language constructs. So for example, here we have a double, which is a data type, and then there is a comment in between, and then there is the name of a variable. And what the compiler does with comments is that it fully ignores them. So the compiler will just look at the comments, throw them away. It doesn't look at those comments. The reason we put comment, though, is for our fellow programmers and for ourselves. Because quite often we write complex codes that might need additional information, not only for the compiler, but also like for our team or maybe for our future self, because we want to write down why we did certain things. Why have we implemented it this way? Why is the constant 7.2 here in that place? What does it mean? Or maybe also a piece of code is really complex because the way we need to express it is really complex. And maybe we want to add a comment, okay, the next 10 lines will do this, but it just looks really ugly the way I've written it, for example. So it allows us to like add extra information for ourselves and also for our team members. There's a third style of comment, which is technically the same style as a multi-line comment, but it has like certain commands inside there. That is a so-called doxygen comment, and doxygen is a technology outside of C++, but it's a very common way of specifying comments, and it has like subcommands like /brief, /param, /return, and so forth, and that allows us to document individual pieces of another entity. So this comment here documents behavior of the function is odd. And here I document that the parameter I here, which is here, it has this meaning, the meaning input. And the function returns true if I is odd and otherwise and whatnot. So that's like a structured style on how to write comments. And if you start out in a larger code base that you work together with members of a team, I would like to encourage you to adopt either that style, the doxygen style, or a similar styles. There are a few other alternatives. Just talk to your team members, figure out what they would like to have and see. Okay, basic types. The C++ language offers a couple of built-in types. And the first one is the Boolean data type, which we write down with the keyword bool. And the Boolean type can store two values. It can store true and it can store false. And the way we declare a variable of a Boolean type is that first we specify the type, and then there is like some white space in between, and then there's the name of a variable of that type. And then optionally, we can also assign a value to it immediately. So this here, the first line, it would declare a variable of type bool that has the name b. And the initial value of that variable is true. And with the semicolon, we end the statement. And that's one line of C++ code. We have other data types, like character, for example, that stores a single character that we put between single quotes. And that is just an 8-bit character. A character is technically an integer, so it's a number, it's a whole number. But 8 bits is just enough to hold characters from the ST data, from the ST character set, which is a very basic character set. There are signed and unsigned variants of characters, which have the keywords signed and unsigned before, and those are especially useful when we talk about integers later. And the signed data type, it has 1 bit in its representation that tells whether the number is positive or negative, and that bit is called the sign bit. So we can put a sign in front of the character, and then character is an 8-bit data type. 1 bit will be used to tell whether it's negative or positive, and the other 7 bits are to tell the magnitude. An unsigned character will not have a sign bit, so I have the 8 full bits for the magnitude of the value, but it cannot be negative. Then this here, char, and then an asterisk here, that declares a pointer variable. And we talk about pointers later, but it's important to see that there's this other construct here that are called strings. And the string is something that I put between double quotes. And that is a list, an array. We also talk about arrays later. It's an array of characters. And that thing here on the right is called a string literal. And then we assign the literal to the pointer variable s of data type character pointer. And that used to be the way in the C programming language, how we used to deal with string variables, that we use character pointers. In C++, there's a dedicated data type for that is called string. And here I can define a variable of type string that has the name t and also assign the string literal to it. And that is a string class that is provided by the standard library. So whenever we have the STL here, that stands for the standard template library, which is the standard library that C++ gives us. Then we have integers, like there's short, for example. And there's a bit of confusion sometimes here because some of the keywords can be left out. So if I declare a variable of type short int, that is the same as short. So like, if I declare a variable of type int and I before put whether it's a short int or we'll see later there's also a long int, for example, I can omit the int. So that is the same. So whether I write short int or short. And short is at least a 16-bit integer. And the same as with character, I can make them signed or unsigned. By default, if I don't specify anything, the data type is signed, except for character, which is a bit special, but I'll leave that out today. But for integers, shorts, longs, if I don't spell out the signed, it is signed by default. So I have a short integer here, so that's a minimum 16-bit signed integer, and I can assign a value to that. And then there is an unsigned short that doesn't have the signed bit, so that's minimum 16-bit integer without a sign. Okay, and that continues for bigger data types. There's int, which is at least 16 bits. On most systems, it's usually 32 bits. Then there is long, which is at least 32 bits. Also, those have unsigned version. So notice again here, I just specified long. I could also say long int, but the int is optional. If I specify this length keyword like long or short, I don't need to put an int afterwards. So long is at least a 32-bit data type. And long is a bit a weird one because depending on whether your program compiles for like a 32-bit architecture, a 64-bit architecture, or for Windows or for Linux, that might really be a different size. So for example, on Windows, that data type is 32 bits, but on Linux, it's very often 64 bits. So that's a bit of confusion. We'll see in a couple of minutes what we can do about this. There's also the data type long. Again, we could also spell it long int, but we can leave out the int here. And there's also an unsigned version. Also notice when I assign a value to that long, I can also specify at the literal. So when I write down a 0 or a 42 in my program, I can also suffix some letters here that tell the value, the data type it should have. So for example, here this is a 0 that should have the type unsigned long. That's what the ULL stands there. And there are also suffixes for the other types, like UL is for unsigned long, L is for long. And the integer is like the default data type, so it doesn't need a suffix. For floating point values, we also have 3 data types, at least until C++ 23. There's the float data type, which is 32 bits wide. And there's a separate standard independent of C++ that describes how those floating point values look like. And that standard is the IEEE 754. That specifies that a single precision floating point value, which is what float is, it should have 1 bit for the sign, then it has 8 bits to store an exponent, and then it has 23 bits to store the mantissa, so the precision of the value. And that's how a float works. And for a double, and double stands for like a double precision, because it's double the size of the float, double the precision of the float. It has 64 bits, and it has more bits also for sign, for exponent, and for mantissa. And then there's also the type long double, and that's again a bit an interesting one, because it depends on the platform and on the compiler what size this data type has. It's at least 64 bits long. On some platforms, it's the same as double, but it can also be 128 bits, so like double the size of double. But on some platforms, it can also be 80 bits, because that corresponds to an architecture that Intel built like some time ago. Like there was a separate coprocessor from Intel, and for some time, the long double used to have the length of that processor. So maybe try to avoid the long double, because it's on different platforms, it has different behavior. OK, I told you because those data types on various platforms and compilers, they might have different sizes. There is a header that allows you to especially request a data type of a certain size. And that header is called c_std_int. And you can include c_std_int. And then you have types available, for example, int8t. And now you know this is a signed integer with 8 bits width. And if you pick the uint8t, then you have an unsigned integer of 8 bits length. And you have those aliases for all the bit widths that are interesting, like 16, 32, 64. Yeah. Those types don't need to be defined. So on some compilers, they're optional, because you could, for example, compile for like an embedded system that doesn't have 8-bit integers. Like those processors are very exotic, but they exist. So technically, the standard is allowed. The C++ standard allows that those types are not defined. But on all the major implementations that you're probably going to deal with, you will have those. So please use those if you need to make sure that your data type has a certain size, which is, for example, important when you want to write that data type to a file and then read that file on a different machine, because then it's very important that the sizes match up. So then please use those data types. OK, I already mentioned literals. So a literal is like a literal number or a literal string that I put into my program. And there are various ways to spell literals, because sometimes I also want to use a different number system to express a number. And by default, if I just spell out digits for a number, that will be interpreted in the decimal system. But I can also use a different one, like the octal system, which has a base 8. It's a number system with base 8. And those start with a leading 0. And that might confuse some people. So please be careful. You cannot just arbitrarily put a leading 0 to a number. It actually changes the base of the number system. So be careful on this. For hexadecimal numbers, we can put a 0x in front. And that means the remainder of the number will be treated as a hexadecimal number, which is a number system with base 16. And because it's base 16, we need more digits than 0 to 9. And that's why we also have A to F to represent the digits for 10, 11, 12, and so forth. So here, for example, that's the number 4D2 in hexadecimal. Why do we need those numbers again? Like sometimes we want to talk to very low-level pieces of the hardware. So it's important that we get the bits right that we put there. And very often 16-bit number systems are easier to express this. Or for example, also using a binary system directly. So with base 2. In C++14, we can also spell out a binary literal that starts with 0b. And then I can put really like the ones and zeros just the way I would like it from the computer to store. Since C++11, I can also put single quotes anywhere in between the number. Those will be ignored by the compiler, but they help us read the code. Because, for example, for decimal numbers, I can put a single quote after 3 digits to group them nicely. The same goes for binary numbers. I can put them anywhere. I don't need to put them every 4th element or so. They just help you for the readability of the number. And they are, again, ignored by the compiler. And we already talked about the suffixes here. If I just type 42, that is an integer. And then you have the U for unsigned int. There's L for longs. There's UL for unsigned long, LL long long, and ULL for unsigned long long. That sometimes matters because you call, for example, a function with a literal, and maybe you want to make sure that that function receives the literal in the right data type. So sometimes this matters. For floating points, and there is a question in the audience. Mike, thank you.
Thanks. The currently discussed only affects the way we input it, not the storage. So the storage will always be like a bitwise representation, or is it somewhere stored?
Yes. So Stefan shakes his hand. Let me think.
Auto something equal.
Oh, OK. The question has even more facets. So when you have a program and you have a data type like int, for example, here. So you spell int I equals something. It doesn't matter how you spell out the number. The moment it is put into an int, this int has a representation that the compiler chooses based on the architecture it compiles for. So in the memory, in the processor, this int will always look the same. But inside your program, before you actually compile it to somewhere, the C++ language has this concept of data types. And data types matter, for example, when you add numbers together, like they could overflow. You could run out of space to store a really big number, for example. So for those cases where you're still in the program is not yet in memory and executing, it matters to the compiler what kind of types you use, because those determine the range of values, whether variables can overflow and whatnot. And Stefan mentioned auto that we're going to talk about at the end of the day.
It's the same for I plus 42, right? It has an effect.
Yes. Which is integral promotion, and we should add a slide on that. OK, questions? Integers look good? Yeah, everybody likes integers. So let's go to the weird ones. Floating points. For floating points, we have lots more literals or ways to spell them. And classically, we'll spell them with the decimal dot in between. So that is the number 12.34, for example. And that is a double precision number. If we don't care about the fractional part, we don't need to spell it. So we can just put a dot here. But it's important that we put the dot. Because if we just write 12, then this is an integer variable and not a floating point value. So the compiler will let you compile that. So if you omit the dot, you throw away the dot here, the compiler will compile this because it clearly sees, OK, this is an integer 12, but you want to put it in a floating point number. So I'll convert that for you. That is fine. It can matter in some other cases. So for example, if you have a number, you divide it by 2, it actually matters whether you want to do the division as whole numbers or whether you want to do this division as fractional numbers, for example. So it sometimes matters whether your literal is also a floating point number or an integer number. So the dot here is required to tell the compiler it's some kind of floating point value. If I don't care about the part in front of the dot, also I can just write .34, and that is still a double precision number. And then we have scientific notations. So those are spelled with an E in between. And that means 12 times 10 to the power of 34 here, for example. So I can use this to express really big numbers or maybe really small numbers. And I can combine this with the dot. I can put like also a minus there to have like a negative exponent, but I can also have like a fractional number and then raise it to an exponent, for example. Digit separators apply, so I can still add the single quotes to separate out the numbers. And here's something very weird, which is called a hex float. You probably never need this anywhere. But if you see a floating point number that looks really weird, it's a hex float, and you Google what it does. Because it allows you to specify one part as hexadecimal and so forth. But I always get the syntax wrong. Go check it up when you need it. Again, we have suffixes here because double is not the only floating point number. Sometimes I want to choose whether it's a float, a double, or a long double, and so forth. So if I add an F at the end, it makes it a float literal. So then the number is the 32-bit float value. I can choose whether it's lowercase or uppercase. I also have, if I don't add any suffix, it's a double precision value. And if I add an L in the end, so that's similar like to the long for integers, it doesn't, so it means a long double here. So that means it's like a double precision with even more bits. It's the long double data type. Since C++23, we'll have a couple more suffixes like F32, F64, and there are even more, like F128, F16, and a couple more. Those are really new, and I'll leave them out for now. There are still some things in the flight about. So, but like in a couple years, you might also see suffixes like those. Okay, couple more useful aliases. So in the header, C_def. So like C standard definitions. There are a couple of more data types, but those are not like primary data types. They're just names for one of the integers that you have already seen. But the compiler is free to choose which of the integers it will use. So size t is an unsigned integer. You don't know which one, but it's for sure an integer that is big enough to hold the size of any data type in your program. So that is useful when you want to ask, for example, for the size of a certain data type, which you can do with the size of operator. When you want to store the size for a piece of memory somewhere, the number of elements in a really big container, for example, that is the size t data type that you want to reach for. But it's just an unsigned integer. It's just one of the unsigned ints that we have seen before. Then insisted int, you can also find the data type pointerdiff, which stands for pointer difference, which is a signed integer that's big enough to hold the difference between any pointers. And the pointer is an address to memory. So the data type is big enough to hold the difference between any two addresses in your machine. And an address is like a location in your memory, in your computer memory. And then there is int pointer and uint pointer, which is an integer that is big enough to hold an address. And then there is a signed variation. So the int pointer is a signed integer big enough to hold an address in your memory. And uint pointer is an integer without a sign that is big enough to, again, hold an address in your machine. So those can be useful sometimes. The most important one is for sure size t. OK, that completes the basic data types. Any questions on those so far? Question in the audience?
Yes, so for the variables, you have like this size _t, or also the slides before int _t. What is this _t?
So this _t, I think that comes from the C programming language, where they used to put this _t on all kinds of aliases. So whenever that was not a type itself, but like an alias to a different type, they wanted to make this clear and add an underscore t to say it's an alias to something.
Okay.
I think that is the convention there. I think you can also see this convention in POSIX, which is like a standard for operating system functions and so forth. We also have lots of something underscore t. It usually means it's an alias to a different type.
Okay. Thanks.
You're welcome. Different question in the audience.
With the suffixes, do you declare the variable and provide the suffix as well?
Yes.
What's the point there? Because
very good, which brings us to auto at the end of the slides. The question was, I can write, let me pick an example. I have like that's a bad, do I have a float somewhere? Or like a long, come on, here. I have a variable that is of type long, but I also assign a value, and I again specify L here for long. Like I'm kind of saying it twice that I want to have a long. Yes, in this case, this is a redundancy. So, and it's not needed. So if I don't specify the L, the compiler will still see this is an integer 0. I put it into a long, it's fine. Yes. It matters when one of the places is not there. So for example, when you don't say this is a long, but you ask the compiler, please choose the data type for me. And we're going to see how that works at the end of today. Or when I don't put in a variable, but maybe I call a function, and in the arguments of the function, I put the number. And then I also I cannot specify the name or like the type of the destination variable. I just have the argument itself. Yeah. And then I need the suffix to tell the compiler, look, this should be an unsigned long, and I want you to pick the function that takes the unsigned long and nothing else. Yeah. Yeah. So then this matters. Yeah, in this case, it doesn't matter.
Yeah. Okay.
Yeah. Question.
Maybe to add to that, when you write 1 plus 2, on the hardware, it's running an integer addition. When you write 1 dot plus 2, it's running a floating point addition. So it's a different hardware that's running the addition. Yeah. That makes a difference.
Yeah.
Yeah, about the size t alias, for example. So I guess one use for that is to make sure that you're not using too much memory or like too large a type. Or are there other uses, or is that even correct, what I just said?
Is the size t data type there to not use too much memory? So I would be very surprised if no, actually, let me think. Size t is a very large unsigned integer. Your implementation, your compiler might provide an integer that's even bigger, but maybe outside of the standard. But usually size t is one of the biggest integer types that you have.
So it's not dynamic, so it doesn't check what it needs.
No.
I see. Yeah.
So like you tell your C++ compiler, I compile for an Intel processor with 64-bit instruction set, and your compiler says, okay, then size t will have 64 bits because that fits that architecture. So the size t data type has a static size that the compiler chooses depending on the architecture. If you tell your compiler, now I want to compile for this little embedded system, the compiler might choose a different size for your size t, but that size will stay constant for the entire compilation and every time you compile again for that architecture. So the compiler might choose a different size, but it will be the same for your entire program. So it's not that the size t can dynamically adjust how big it is. Yes.
Thanks.
You're welcome. More questions?
So you mentioned the pointers and this pointer difference. Okay, so you explained this pointers to be kind of an address pointing to something.
Yes.
And this pointer difference. What kind of quantity is this? I mean, how can I imagine a difference between two pointers to look like, and what do I need it for?
Okay, let's readdress the question in a later chapter. We talk about pointers in a bit. If the question is not answered after the pointers chapter, then please raise it again.
Yeah, sorry, my question was similar. Like I just wanted to know when, like I do have a basic understanding of what pointers are, but I can't imagine a situation where the programmer is interested in the difference between
two pointers? Like when would this matter?
When would this matter?
From the user end, right?
Yes. It matters when you have, let's say, a function and you want to give the function a piece of memory. And you describe this piece of memory by giving it a pointer to the begin and the end of that storage. And then let's say you want to know how many bytes are in between there. And then, or how many integers are between the start and the end of this memory region, for example. So you're interested when you deal like in memory blocks that are described by like begin and end pointer or so. So there, this is something where it comes up. Yeah. Yeah. Okay. I guess we continue because we'll have break in 22 minutes or so. And I have been told the break is sharp because we're going to get coffee and croissants, I think. So we got to finish on time. And we still got lots of stuff to cover. OK, so let's address those questions about pointers. And let's talk about arrays and pointers. And we will talk about arrays first. And specifically static arrays. So arrays of a size that is known at compile time. And the first line here, we've seen already before, that's an integer, that's the name of the variable. But what's new here is that at the back of the variable, I can use two square brackets, and I can put a size in between. And that tells the compiler, look, I don't want to have just one integer, but I want to have many integers that are just placed one after each other. And that is called an array. And in this case, the array has 4 elements. And I can also initialize this array by providing values for all of these places in the array. And I need to wrap those array elements in the curly braces, as we have here on line 1. Because the compiler is smart enough to count how many numbers I put on the right side, I don't need to put the size of the array in the beginning. The compiler can just figure out how many I have. So that is fine. This is still an array of a static compile time known size because the compiler figures out how many there are. I can do the same for characters, and then I can just make an array of characters. You can, in fact, make arrays of arbitrary types. So I don't think we have examples of that, but later when we get to know more data types, you can make arrays of all of those. There is one shorthand notation. That's when I have a string literal. So when I have characters that I put between double quotes, the compiler also treats this as an array because, in fact, it's an array of characters. But there is one peculiarity. It's because the compiler will insert, after the last character of my string literal, it will insert a 0 character. So a character with the value 0. And that is the so-called null terminator. It will end the string literal with a 0 byte, a 0 character. And that is because in the C programming languages, the way strings work is that you pass around the start of the string. So we talk about pointers in a bit. So you pass around a pointer to the beginning of the string. And then what you would do in your program, you start reading from that address. And the string goes until you reach one character that is 0. And then you know that's the end of that string. And that's how strings in C work. You need to know the beginning. And then you scan until you find a 0. And in fact, we can just spell it out differently. So here we can also describe an arrow and put the characters individually, one after each other, and then specify the 0 ourselves. And those two initializations are the same. So whether I use the string literal and the compiler inserts the 0 for me, or whether I spell out all the characters myself, it has the same result. It has the same representation in memory. The string literal up here is just the shorthand notation for our convenience. OK, I can then, if I have a variable of an array type like AI, I can subscript it. And this means I can put a number in the square brackets and ask the compiler, please hand me out the variable at the position 2. And the position 2 here starts counting from 0. So 0 would be the first place in the arrow, 1 would be the second place in the arrow, 2 would be the third place in the arrow. So counting in C++ for arrays starts at 0. And if you look at the definition of AI, it has the numbers 1, 2, 3, 4. So getting the third element, so the element at index 2, that would give us a 3 here, that 3. OK. The compiler allows us to put numbers here that are outside the range of an array. But this is an error. So when you do this, your program, how can I phrase this nicely? It exhibits what we call undefined behavior. So it's outside, you made an error in your program, and now your program can behave in undefined ways. And one behavior could be that you'll get out a value that is just some random thing that happens to be in memory there, but your program can also crash. Or it can continue and then crash somewhere later. The moment you have like an error like that, is like your program somewhere down the road can just fail in any way, and nobody gives you any guarantee on what happens. So that's something that you need to be very careful with, that when you have arrays, that you don't access those arrays out of their bounds. So the AC array here, the array of characters, it has 3 elements, or here has 4 elements. But if I access it at the 8th position, that is outside the range of the array. And that is an out-of-bound access, and that can cause crashes or any behaviors in your program. The same is with the array AI. That has 4 elements. So the valid indices run from 0 to 3. So the 4th element is already outside of the array. That's also important. 4 is the size, but 3 is the last index of this array that is valid. OK, let's talk about pointers. And I think I have a really cool animation here. So we'll see like a piece of memory here, how it's laid out in our machine. And the memory in computers, they typically have addresses. So this means like each cell of your memory also has a number that identifies the cell in the memory. And this is basically what pointers are. They just contain those numbers, those addresses that refer to the cells in your memory. So if I declare a variable I that is of type int, and I assign it the number 4, this variable I gets placed into memory. So it's put into memory down here, and it carries the value 4. So the number 4 is written in this place in memory. If I now create a pointer to that variable I, and there are 2 pieces here. The first one is I declare as a data type an int star or an int asterisk. And that means I have a pointer variable to an integer pointer. I give it a name, it's called pi, and the value of this pointer is now %i. And the ampersand here means, please give me the address where this value is stored in memory. So those are the 2 pieces that are relevant to pointers, is that you want to get the address of something else, and then you store this address in a variable that has a pointer type. And the way this is placed in memory is that you will have a variable pi in memory, but the value inside that memory cell, the value of the variable pi, is the address of a different memory cell where the variable I is stored. Is that OK? Sounds good? Yeah. OK. So let's continue from here. I can then declare a new variable j. Also, the variable j needs a piece in memory. It's placed here next to our other variables that we already have. And now I can dereference a pointer. And that means I take a pointer variable, I look at its address, and I go to where the variable points and read the value from there. This is what this asterisk before this variable of a pointer type does. It means it's like take the variable pi, which is here, take out its address and go there. So we look at it. It's the memory cell 3000. So we go to that memory cell, and we read out the value that's written there, which is 4. So this here, dereference pi, that evaluates to the value 4. It goes to that address, takes the 4, and that's what it returns. And then I just add the number 1 to it, and I put that back into the variable j. And this is why the variable j here has the number 5. That is dereferencing a pointer. Question?
So I just wanted to ask about what happens to j if you don't dereference pi there. Since pi is still an integer, it would add 1 to that integer of the address, I guess, right?
So no. And
Okay.
the reason is because C++ has a type system that doesn't allow you to do this. Because the C++ compiler knows that the variable pi is of type integer pointer. And pointers, even though they use addresses which are numbers, like in the type system of the language, a pointer is something different than an integer. There are some ways you can use them two together, but in that case here, the compiler will see if you omit this asterisk, the compiler will see, okay, you take a pointer, you add 1 to it. That itself is okay. That would give you a pointer to the address after it. But then you write a value that is of pointer type into a plain integer, and the compiler would say no.
I see.
I'm not letting you assign a pointer variable to a plain integer, because those are two different things.
Cool, thank you.
And I think that's even down somewhere as an example. Yeah. Okay. So let's continue. Maybe some questions will clarify them. If I create a variable of an array type, like AI here, for example, that is basically 3 integers. So those will be put in memory one after each other. So AI 0 with the value of 1, AI with index 1, which has the value 2, and so forth. And now I can declare another pointer variable and assign that array to it. And this is a point of frequent confusion, because an array and a pointer are two different things, but in some places the one just collapses into the other. And this is what happens here, is I have a variable of array type, and I assign it to a variable that has pointer to integer type here. And what the compiler does is it will just take the address of where the array starts, which is the address of the first member of the array, and it will put that into that pointer variable, PAI. So this PAI, because it's a variable, it has its space in memory, and it will contain the address of where that array starts. And that is here. Notice we still have like all the space for the array, and also the pointer takes its own space in memory. But the pointer stores the address to where the array starts. Now we can take that address where the array starts, PAI, this one here, and we can add 1 to it. Notice I don't dereference the pointer. So now I'm actually reading the address and add 1 to the address. And I put this into a new variable. So here I have a new variable, PAJ, that has a value that is the previous address, this PAI, plus 1. And now notice that if I take this address and I add plus 1, this is not this value. So actually what happened here is the address jumped by 4 and not by 1. And the reason for this is because the compiler sees that this PAI is a pointer to integers. So it knows the size of one integer, in that case, is 4 bytes. So actually like 4 addresses. So when you add to a variable of a pointer type, the compiler will always add or subtract in quantities of the size of the type. So here, because PAI points to integers, if you add 1 to it, it will increment the address by the size of one integer. And that's why between the two addresses, we actually have a difference of the size of one integer and not just the number 1. So pointers, increment, decrement, it works in the sizes of the data type. So now I can go to PAJ, which is here, that address. And now I dereference that again. So I go to where it points to, which is over here. That's the array at index 1. I read out the value, and I add 1 to it. And that I store in a new variable k. So here I have a new variable k, and it has the value 3. Because this is what I read through the pointer PAJ. I went over there, I got the 2, and I added 1 to it and stored it here into k. Okay. The compiler prevents us from, because this is hard, and we can easily confuse some stuff here, the compiler prevents us from some common pitfalls. And one of them is if we mix up normal numbers and pointers, like some of the question before. So if I take the variable k, which is just a plain integer, and I assign this plain integer to a variable that has a pointer type, the compiler will say no. I don't let you do this because the integer and the pointer are two different things. but I can force the compiler to do it. And that here is a cast. I don't think we'll talk about casts later, but this is a way to tell the compiler, look, I'm serious, really, really go and do it. So the compiler says, I'll trust you. You get what you ask for. So this here will create a pointer variable, PAK, and it has the address free. So that is not the number free, but actually the memory cell with the address free, which we see here in our memory. It's not here. So it's actually a bit unclear to where does this point to. And on some machines, like the address free may actually exist. On some machines, it might not. It might be somewhere inside your operating system or like in a protected part that your BIOS uses, for example, of your computer. So dereferencing that address is very probably like a crash in your program. But again, like we do a programming error here. So afterwards, all bets are off. The program might continue. It might just read a random value out of something. It might crash. It might crash further down the road. We don't know. So this is an error. And that's why the compiler prevents us from doing that. So whenever you explicitly ask the compiler, no, I'm serious, really do it, maybe think twice. Is this really OK? Is this really what I want here? Because the compiler tries to prevent you from doing some of those things. OK. There's a special pointer value, which is null. And that is a pointer to nothing. It doesn't point anywhere. And I have a keyword for that that is called null pointer. It's written null PTR. And I can set a pointer variable to this null pointer. And then it carries an invalid address. So an address that specifically tells this pointer should not point anywhere. In earlier versions of C++, we used to set pointers to 0, or there was a macro called null, all in uppercase. Don't use that anymore. If you see it anywhere in your code base, you might want to rewrite it into a null pointer. Because those here are plain integers, and that has like an effect. For example, we can write buggy code with this. Here's an example. I have a pointer to void. We haven't discussed void yet, but void means, it's quite funny actually. Void means nothing. So functions, for example, can return void, which means they don't return anything. But if you have a void pointer, that actually means it points to anything. And you don't know what it actually points to. So you can set that void pointer to null, or you can have just the plain integer pointer and set that to null pointer. That is fine. You can also set an integer variable. Notice there's no pointer. You can set it to null uppercase, because the null macro was just a replacement, was just an alias for a 0. So that will compile, but it's probably not what you wanted, because maybe you forgot to write your pointer here, and maybe you actually meant I to be a pointer variable. But if you use null pointer, the compiler will tell you, wait, what? You have an integer on the left, you have a pointer on the right, you probably messed up something here. So that's why it's preferable to use the null pointer constant. OK. One last word on memory management in C. So the C programming language also had functions that allowed you to create pieces of memory, destroy them, initialize them. And I'll just give you a very quick rundown how they work. There's the function malloc, for example. And for malloc, you pass in the size of the memory. You don't tell it how many elements you would like to have. You tell it the size in bytes that you want to have. And you get out a pointer to that area of storage here. But because everything is like treated in byte quantities, and you always need to explicitly, after you requested a piece of memory with malloc, for example, you must never forget to explicitly release that memory again. And because this is error prone, we don't recommend to using those anymore. You may see them here and there in a code base or so it's important to understand what they do. But don't use them anymore in your code. There are better alternatives in C++ that we discuss later during this week. One of them is std_vector, for example, or smart pointers. I hear a phone or so. OK.
I have a question.
Yes, let's cast a couple questions, because I assume the coffee will come in a couple minutes. Questions on pointers and arrays.
In what real situation we are going to use a null pointer, a pointer that doesn't point to anything?
and null pointer. When would you use a null pointer? So null pointers are quite useful when you want to build data structures, for example. So you say, an example is like you have a list of some items. So you say like, I have some kind of structure, I put some data, and then I put the pointer to the next piece of the data structure. And that next piece of the data structure might exist or it might not exist. So this allows you to like dynamically choose how long this chain of pieces can be. So you say like, until that pointer in one of the pieces is null, the data structure continues somewhere. You might also have a function that takes a pointer as an argument, and you use that to make a kind of optional argument. So sometimes you pass it to the function and sometimes say, okay, look, there is no additional value. I'll just pass null as a function argument, telling the function, look, this thing is not there. So you can use it to express a thing that is there or not there, to express optionality. But there's also a different construct in C++ that you can use instead of that. We'll talk about that in the advanced course. Okay, question in the audience.
I noticed that when you were declaring the pointers, like a couple of slides back possibly. So
here,
what I'm saying, for example, int space star pi.
Yes.
Yeah. And then a couple slides later.
I know what you meant.
Yeah.
So like sometimes we put the asterisk on the right and sometimes we put it on the left side.
Is there a difference?
Yes. No. So
Okay.
there is no difference between those two. It's just different. Like it's a matter of taste. Like some people prefer to put it on one side and one on the other. Stefan Hageberg always says that he likes to piss off both worlds and put it in the middle and put a space in front and afterwards. So also that is possible.
Okay.
In general, come again?
What we say is both are equally unhappy.
Yes. So actually in many places in the C++ language, the white space is irrelevant. So a lot of C++ source code can actually be arranged in various ways because the compiler just cares whether there is at least one white space. And in some places, for example, between a keyword and some kind of symbol, the compiler doesn't care at all. You can put 15 tabs and spaces in between, compiler doesn't care. In many places. In some places it matters, but in most it doesn't.
Yeah, that's fine.
Good. So
coffee has been served.
There is coffee already.
Yes, it's
Okay.
outside. So we can either have one or two more questions, or we take, according to the agenda, 30 minutes.
According
for a
to the
break.
agenda, we have 30 minutes of break, but I took a bit longer than I expected. So maybe we cut the break a bit shorter. What do you think? 20 minutes? Let's
That
see
would
whether
be-
everybody is back at 20 minutes.
No, for the people in Zoom, we need to tell them a time. So at 10:35, we're back.
Okay, cool. Let's try for 20 minutes. And if there's too much croissants and you need longer, then it will be a couple minutes longer. Okay.
All right.
Enjoy your break. Und ich habe mir zu Hause gedacht, weil ich habe meinen Vortrag vom letzten Jahr angeschaut und habe mir gedacht, boah, ja, thanks. Und wir haben letztes Mal Scopes und Namespaces noch gemacht und ich habe mir gedacht, oh, diesmal müssen wir schneller sein. Und jetzt haben wir langsamer Scheiße. Okay. Na, ist gut, wenn wir die Pause ein bisschen... Okay, people are slowly coming back. We'll resume in a minute or two. For the people here in the audience, I've just been told that we're actually not allowed to bring stuff inside, like food and drinks. I asked last week, and somebody told me it's fine. So I'm confused now. So my recommendation now is like, don't spill anything, because otherwise we get in trouble. So and you're the lucky participants, because next time we'll probably not allow it. So enjoy, and please don't spill.
You know, the rule is that you're not allowed to bring it into any meeting officially. In practice, you can bring it.
Okay, now I learned something. Because I always bring my stuff. Maybe. I wonder whether they can send it to me. Like, I don't have a full CERN contract. so we can find out. No. Now I know who you are. So I'll forward the bill to you. Okay, can people on Zoom hear us again?
Yes.
Would somebody on Zoom? Okay, I heard a yes. Nice. Okay, then I'd like to continue. From now, we will go until 12 o'clock, I think. So that gives us roughly 1.5 hours. We still have lots of material to cover. Yeah, we'll see how it goes. Anyway, any questions until so far? Actually, the break was pretty good because pointers is one of the hardest things. So everybody could relax afterwards. Nice. Okay. Next one will be a bit easier. We'll talk about scopes and namespaces. And a scope is the portion of your source code where a given name is valid. Because in your program, you will declare lots of names, lots of entities, variables, functions, classes, and so forth. And when software projects grow really large, it's important that you can kind of limit where this name exists, where it applies. And that is what it's called a scope. And simple scopes, they're just within opening and closing curly braces. And one example here on the bottom, I can open a curly brace and then declare a variable A. And then I can open another curly brace, declare a variable B here. And inside that inner scope, so on line 2 after the declaration of B, the names A and B are valid. Both names are within scope. That's how we call that. Because scope nest and outer scopes are always visible inside in inner scopes. But the moment we leave a scope, so at the end of the scope where B is defined, so out here again after line 3, only the variable A is defined again. The variable B was in an inner scope that has ended, so it's no longer visible. And there's also one global scope, and that is the scope of your entire translation unit, which is basically your CPP file and all the header file that it includes. That is the one big global scope. And within the global scope, you can declare nested scopes where your stuff lives. And those scopes, they also have an influence on how long variables live in your program. So when they become visible, but also when they end, when they cease to exist, when they are destroyed. And that is what we call the lifetime of a variable. And variables, they're allocated when you define them. So when you define a variable like this A here, int A equals 1. The moment this line ends, the compiler will reserve a piece of memory where this variable A lives. And that variable A continues to live until the scope where this variable A is defined ends. So on the very outer part of our program, here we are in the global scope because there's no other scope somewhere else. That variable A will live starting from there until the end of our program. But if we open another scope here with the open curly braces and we declare a variable B inside here, when that scope ends, then also the variable B ceases to exist. And I think I also have like this animation here is we declare an array of 4 integers. Those, by the way, don't have any value. I didn't provide an initializer, so the values are undefined, can be anything. And then I can set this the 0th element of B to 1, because that's what was written in A. And the moment I leave this scope, the variable B no longer exists. In practice, because your program writes stuff to memory, and when a scope ends, the program doesn't go to memory and starts cleaning up, because that would be too slow. Those values very often remain in memory. But it is an error to go there to reach into memory or to reach into a place where a variable used to live, but it doesn't exist there anymore. That's what's sometimes called a use after free. And that is also a programming error. And very often, the compiler can catch you doing that. So for example, if you would try to access B here, it tells you, no, it doesn't compile. There is no B in this scope, because B used to live in a different, smaller scope that ended. So there is no B anymore. A piece of good advice here, it's always good to initialize the variables when you declare them. So when you declare a variable A, also make sure that you assign it a value to it, because that gives your program a deterministic behavior. Because if you forget to initialize and maybe you read from the variable somewhere later on, your program might not be deterministic, and it is a programming bug. Question? Do we have the mic again?
if I initialize the variable, does it has any cost, like a +1 instruction or something like this?
If I initialize the variable, does it have a cost? Yes, because the program needs to write that variable to that piece of memory. Yes. Which is the main reasons why programmers sometimes don't initialize, especially when you create a large piece of memory. Then sometimes you leave it uninitialized because you know I will later overwrite it. But if I initialize it now, I'll actually pay for this extra cost, which is sometimes a reason not to do it. But please only do this if you provably know that it has a performance cost. Question?
On one hand, I just wanted to collect it, but also to comment on this. There is a performance cost, but most code checkers these days even warn you about uninitialized variables because it is just bad practice not to do it. And for instance, in the Atlas code base, we decided a long time ago that even in places where we knew for a fact that an uninitialized variable would eventually get initialized because of the structure of our code, we still ended up initializing them everywhere explicitly, in case your software framework starts doing something funky and doesn't initialize it after all. So it's not just to underline it that the argument that, well, there is a bit of an overhead with writing 32 bits or 64 bits into memory, that's a tiny overhead, and that should not guide you in how you do this.
Question?
This maybe pushing a bit, but you can, from the last slide you showed before the break, you can still cheat this, right? Because you could get a reference in there.
Yes.
And does the compile protect you against this?
No, sometimes. The question is, I can cheat this because I could, for example, declare a pointer to an integer outside here. I create inside the scope my integer array. Then I assign an address of that variable to my pointer that lives outside the scope. Then the scope ends. And then I still hold a pointer with an address that points to back where the variable b used to live, but it's no longer there. I can do this. It's a programming error. Like the compiler may sometimes, if it sees the whole function, tell you, oh, you're referring to something that's out of scope. But in some cases, if the code is complex, the compiler may not be able to prove that. And it is a programming error. So please don't do it. There are some tools, I think, in the advanced course, like address sanitizer or so, that can help you find such kind of bugs. But don't do it. It's actually like one of the things in C++ is you should think really careful about the lifetime of your variables. Make sure also when you take pointers or references to other variables that you know very, very well that the thing you're pointing to for sure exists long enough as you hold that pointer to it. That's a very frequent source of programming mistakes, getting the lifetimes wrong. Okay. You want to say something? No.
I mean, to add maybe is the philosophy of C++ is that you don't pay for something you don't use, right? But also this gives you the license to shoot yourself in the foot. So it's made for speed, and you can use it in a safe way, or you can completely mess it up. It's up to the programmer.
Yeah. This is why we have so many tools for debugging issues, because, well, there are many ways of shooting yourself in the foot.
Okay. Then I'd like to continue here and talk about namespaces, because so far we've only seen like an unnamed scope with open and closing curly braces that you can put inside a function, for example. But I can also assign a name to that. And that is a namespace. And that allows you to segment your code and give a name to certain parts of your code. And the way you spell this is with the namespace keyword, then the name of the namespace. And then again, you have open and closed curly braces. And those make up the segment of where entities inside that scope, they need this extra name so you can distinguish them from other variables. An example we have here is we declare an integer a in the global scope. And then we open a namespace n and declare another integer variable a here. And those are two different a's. Those are two different variables, because the one lives in the global scope and the other one lives in the namespace n. Because the namespace separates the entities inside it from other namespaces. I close the namespace, I open another namespace, I call it P, and I declare another integer A. And that doesn't clash with the other two A's that already existed there. So now we have 3 A's, but those A's live in a different context, in a different namespace. I can also nest namespaces. So inside the namespace P, I can create a namespace inner, and I declare another A here. It's a different A. Now I have 4 A's, but they live in different places. Then I declare a function f, and inside this function f, I want to refer to one of those A's. And because there are separate A's to choose from, I need to tell the compiler which one do I mean. And in that case, I can prefix this n : : and that means go to the namespace n, or like to an entity n, and try to find an A inside that. So that n : A will refer to this A up here. And then I can assign it the value 3, for example. So this : it separates like an entity and then the thing where it lives inside. So in that case, we use it for namespaces. It can also be used for classes that we'll see on Wednesday. Question? Thanks, Attila.
May I ask if I add to the line 11 using namespace n, and then on the next slide, on the next line, I would use using namespace p. I understand that it is a very bad practice, but
yes,
is there a rule of which a then would be picked, or is it ambiguous?
No, and we'll talk about that on the right side of the slide. Okay, so just wait 30 seconds. Okay, then let me finish the slide. Here, open a namespace p, and that namespace p was already opened before here. And that is fine. So I can reopen a namespace and add more names, more entities to a namespace that was already declared. And now I declare a function f here. Notice this f is a different f than the f that exists outside in the global namespace. And now here are a couple rules. So I can use the a inside the namespace p. So inside this namespace p, there is no a, but in the previous namespace p that I reopened, there is an a. So this p : A will refer to the A that's over here. Okay, that's okay. But because the function f is inside the namespace p, and if I don't qualify the variable a, the compiler will first start looking for an a inside its own namespace. So it will still go to the same a over here that is inside the namespace p, because the function f is also inside namespace p. So when I don't tell the compiler where to look for, it starts looking in its own namespace first. And then it goes up into namespaces around that namespace. If I want to refer to the global namespace, I can just write : and I don't put anything in the front. That refers to variables in the global namespace. So the one at the very outside here, that's the A on line 1, because there's no namespace around it. It's a global namespace. Then I just use : to refer to that. I can also use p : inner : A. So that looks for a namespace p, tries to find an inner. No, there is no one here, but there's a namespace p, and there is an inner inside, and there is an a. So it's going to be this a that I referred to here. I can also omit the first namespace, because when the compiler looks up for inner, it will look inside p. Is there an inner? In this p, okay, inside this namespace p, which is my own namespace, there is an inner, so I can go there, and I can look, there is an a inside. So this line 19 and this line 20, they refer to the same a, because the compiler will figure out, because I'm already in namespace p, it will find this inner even without qualifying the p before. And if I want to refer to the a in namespace n, then I need to put name n before. So the compiler will look for an n inside the namespace p. There is no n inside there, so it will leave the namespace p, look in the global namespace, find the namespace n there, and then find the a inside that namespace. And now to the question that we had before. There's also a using declaration, so I can take everything that's contained inside the namespace and make it visible outside the namespace. So with a using declaration, I can pull all those names that are inside a namespace into the namespace where the using declaration appears. So this using declaration is on the global scope, in the global namespace. So I can take everything that is in p inner and make it also visible in the global scope. And now I have a function g that refers to an a. And now the compiler will find the a in the global scope, but it will also find the a inside p inner, because that a was made available via this using declaration. And now the compiler will tell me, look, there are two A's. I don't know which one to choose. So this is an error because it's ambiguous. The compiler doesn't know which one do I mean. Does that answer the question? Perfect.
So yeah,
Question.
there is no preference in this case. And just to add that, as it was said, all of these scoping, this is one of the things you have to learn in C++, what scopes various names are valid or not valid. Things even get more complicated, even in this example, and I was wondering whether to even mention it, that the function f is its own scope as well. And if you start declaring stuff inside of the function,
yes, I could have an int a here.
Then you can end up with just compiler warnings, because certain name clashes, the compilers these days even warn you that, okay, this is probably what you meant, but if you would declare an int a inside the function, that would compile, but that would give you a compiler warning that you're hiding a variable.
Your shadow,
and
yeah.
You probably didn't want that. For the namespaces, you do not get a warning. So that is on you to know at all times what is in which scope.
Thanks. So I'm wondering now, what is the better practice to either use the namespace or not? I mean, the full namespace with all separator, instead of using namespace and then whatever I want to.
The practice. I'm trying to think about the context of that function. So in principle, you want to use namespaces, especially if you work together with other teams and you're contributing to a larger code base, because it's important, because you will amass a lot of code so that your entities don't clash with each other, that you use namespaces to encapsulate certain regions of your source code. That is important.
No, but I think the question is a little bit different. And I think the answer is it depends. Because in certain cases, it can be a super powerful tool to change the behavior of a piece of code by, if you have some piece of code inside namespace foo, which uses some types without explicitly declaring that which namespace those types should come from, but by default they come from namespace, the global namespace. Then it can be quite a powerful thing to just inject a type name before, let's say, a function into the namespace foo, and then use a type which is maybe slightly modified compared to the global namespaced one. I'm saying this because I use this trick sometimes, but it's really just sort of a trick once you're doing some really complicated class designs. Normally, I would say that inside of, especially implementation files, inside of CXX files, it's usually a good idea to just use the minimum namespace for your declaration, because as long as the code is meant to be clear on which type you mean, the shorter you can make your code, usually the better. Well, this also depends, but being extra verbose just for the sake of being extra verbose is usually not worth it. But again, lots of shades of gray on this. In such an example where you have 4 different objects with sort of the same name, yeah, in this case, you would want to be as verbose as possible because, well, this is a super confusing setup. But normally, we don't try to make our lives this hard.
So also another piece of advice is that even though it might hurt readability, like adding the explicit qualifiers, you can mess up less than if you put like lots of using declarations in the beginning of your file, because then it very easily becomes ambiguous of like what happens in your source code. So qualifying is usually safer.
Oh,
yeah.
That's an excellent point. I really only meant leaving off qualifiers when you are in the same namespace as the type that you're referring to. Using namespace in general, you should be very cautious about.
Very conservative, yeah.
Very conservative about. But yeah, when you're in the same namespace, then you should feel relatively free to leave off the full qualifier.
So we had, in the meantime, 2 questions on Zoom, but also looking at the time, we have to speed up a bit. So there's very quick answers to the question. So somebody asked if you are you moving those things into the global namespace? And the answer is no, you're not moving them. You're making them visible. They still stay where they are. Okay, but they're just usable. And the other one was how to resolve the ambiguity while you fully qualify the name. You just mentioned the full namespace, and that's how you do it. But you have to go until slide 70, until 12 o'clock.
Yes, so it's nice to have these discussions, but we also have a lot of slides to pull through. So please continue with questions, but we try to answer them more shortly now. Okay, namespaces can be nested. We have shown this before. Since C++17, there's also a shorthand notation now. So you can write a namespace and then like separate multiple names in between of colons, and that will open several namespaces within each other. It's a shorthand notation. That's something to be aware of. Okay, that's it for scopes and namespaces. Any final questions? Good, perfect. Okay, then let's talk about class and enum types. And we start with structures, a struct. And a struct is a way to group multiple variables or multiple data types together into a single unit under one name. And I've put here an example, which is a struct called individual, and it has 2 what we call data members. So it groups 2 variables, age and weight. And age is unsigned character, weight is float. So those 2 variables are now one thing. And that makes sense sometimes in the design of your programs, because logically some things might belong together and you want to handle them together. You want to pass them together to a function, return them together, and so forth. And I can like create variables like we have seen with integers before by again using the type name on the left. So I use my struct individual that I declared up here, and then I put the variable name. And this will now reserve space for both of them. And I think I also have, again, an animation here, or like this visualization. And the way I access the variables inside my structure is by using the variable of the whole struct, and then I write dot, and then the name of the data member inside the struct. And that will refer to the part inside of my structure that I declared up front when I declared the structure. So here I can set the age of the student to 25 and the weight of the student to 78.5. And in memory, the way this looks like is that the compiler will reserve memory cells for all the data members that I have in my struct. So here I have, because age is an unsigned character, it's 8 bits, it will reserve 1 memory cell here. By the way, one such cell is 4 bytes big. So it will use the 1 byte in the front to store 25. And because the float is 4 bytes wide, it will reserve that part and store the floating point number. Notice that there are 3 bytes which are undefined. And the reason this is because floating point values, since they're 4 bytes, they should be placed at an address in memory that is also a multiple of 4 bytes, because this is usually how processors can handle them faster. And that is called alignment. And this is why we see here 3 empty bytes here. This is usually handled by the compiler, and you don't need to worry about this. There's also a second version how to create an individual. I can also open the curly brace here, and then just in the order that I declared my data members, put the values. And the compiler will initialize one after the other with the values that I put here, one after each other. There's also a bit of special syntax with pointers. So as with like integers, as we've seen before, I can create a pointer to a structure. So again, using the ampersand, I take the address of that student in memory, and I put it into the variable pointer that is of type individual pointer. Individual is the struct name. The asterisk says it's a pointer to one individual. Let's see if I have that here. No, that shows the teacher, how it's placed in memory. Do I have the pointer? Yes. So that pointer variable here that lives up here, it stores the address of where the struct starts in memory. So similar as with arrays, where a pointer to an array points at the start of the array, a pointer to a struct points to the beginning of the struct in memory. And here's a bit of special syntax. When I want to access a data member, now there is this arrow operator. So I can use a pointer to a struct and then arrow and then data member, and that's how I can access parts of the struct. And this is just the shorthand notation for first dereferencing the pointer. So I go to the beginning of the struct in memory where the pointer points to, and then I go to that sub-data member that I designate with the name here. Good. Similar to structs, unions, they also have a name and they have data members. But instead of a struct where I store all the data members next to each other, the feature of a union is that it stores the data members over each other. And that has interesting implications. And I create the three variables here, D1 until D3 of type duration, which is a union. And I assign from D1, I assign seconds to a value. So this will create space for the union and will write that value here. But I can write the hours of a different variable. So this variable D2, it lives up here. I only write hours, and hours is a short. So in our case, it's 2 bytes. So it will only write the 2 bytes of storage and put the 72 here. And for the duration D3, I only write the days. So it will put only the days here in the 1 byte, which is denoted by this character data type. And the size of the union itself is determined by the largest member that is in the union. So the compiler will reserve as much space to store the largest data member. But if I assign to a smaller data member, it will just use the portion that it needs for a smaller one. The union is still as big as the largest type. And if I now write to the days members of D1. So for D1, we first wrote the seconds here. And now I write to the days member. I write a 3 here. Then now I have a 3 in the first byte, and the remaining bytes there are undefined. It could be parts of the second that I wrote before, but it might not be. So the C++ language leaves it open what is still written there. And if I now read out the seconds again, so from D1, where I previously wrote into the days variable, now I read out the seconds, this is undefined what's going to happen. You will maybe read some bits, your program could crash, it's undefined what happens. So with unions, you need to be very careful that if you write to one of the data members, you also must read out again from the same data member. There are certain ways outside the standard you can abuse this. So you can like read into one part, read out from a different part. So some compilers allow you to do that. But inside of the strict C++ language, you should not do that. Attila.
I just want to quickly mention that you guys should know about union because this is one of the base types of the C++ language. Don't be worried if you are a bit confused right now, because throughout all my life, I used unions a very countable number of times in my code. Because usually you really only want to use such a type once you are doing something really specific. So yeah, know about it, but don't be worried if some of the explanation is not super clear right now. In your everyday world, everyday work, very unlikely that you should be using it.
Yeah. Starting with C++ 17, there is also a better alternative. I'll come to you in a second. If you need to store one of many alternatives. So if you want to have a data type that can be either seconds or hours or days, in C++ 17, we have a better way to express this. And this is the variant. Question?
I didn't understand the difference between a struct and a union.
Yes.
Really, because
so it's the way that the compiler places the data into memory. For a union, it will overlap the data members. So it will take the integer variable and then put the short variable into the same memory. So they're all on top of each other. And you can only ever deal with one of them.
So the idea with a union is that you declare what that variable might be. At any given time, that object in memory, where you said duration D1, D2, D3, those are one of these types. The compiler and the runtime knows which type at any given point it is, but it might be either an int or a short or a character. It's not all of these at the same time. It's always one of these. With std variant, this is a bit clearer, and std variant provides you nice ways of even asking it, okay, what type are you actually right now? What's the last thing that somebody said to you? As I said, this, in some cases, it's a very useful type, but usually we really only used it in core software pieces where our software framework was doing something very specific. In, let's say, physics analysis, if I see somebody using a union type in a physics analysis code, then I know that they did something bad.
Okay, so bottom line is use unions very sparingly, if at all. Like very often you don't actually need them, but they might show up somewhere. Okay, enumerations. Enumerations are a construct that allow you to declare a couple of constants that are related to each other. And here's an example. For example, I want to declare vehicle types. And one type of vehicle is a bike, the other is a car, the other is a bus. But those constants are kind of related to each other. They all describe a vehicle type. So I can group them together and give them a name, which is called vehicle type here. And then I can also create a variable of type vehicle type and assign one of the constants here. With C++11, I can also specify what type the compiler will use underneath, because basically those constants will be described inside your processor just as plain integers. So this is like a nice syntactic way to create constants that are just integers. And those names bike, car, and bus, the compiler will assign integer values to them, usually starting at 0. Although you can choose. You can also tell the compiler that, okay, bike should be the value 3, car should be 5, bus could be 7. And it makes it nicer to spell bus in your code than writing 7 there, for example. If you don't specify the underlying type, the compiler will choose one for you. So sometimes it's nice to specify it because your enum type is maybe written to a file and read on a different system. So you want to influence the size of that. One peculiarity is that those constants, they're available outside the enum without qualifying it with the enum name. So you see that actually the curly braces that compose the enumerator values, they don't open a scope. So this constant car here, for example, you can just use it outside the enum. And that can sometimes lead to problems, which is why in C++11, there is a new kind of enum, which is called the enum class, or scoped enumeration, where you can additionally put the class keyword after the enum. And now those constants inside are properly scoped. Now you need, if you want to access the car enumerator inside here, you need to prefix it with the enum name. Otherwise, you'll get a compile error. The compiler will tell you, I don't know a car in the current namespace or in the current scope. There's a second advantage with scoped enumerations, and that is they are stronger in the type system. And I'll have an example here. I have just the plain enum, the one we had on the previous slide, and it has two enumerators, bus and car, and I have an enum color with red and blue. I can now create a v-type for vehicle type T and assign it to bus. Note again, I don't need to prefix v-type here because it's the classic enum. I can then compare this T, which is a vehicle type, to the color red. And that is fine. The compiler will let us do that because red is basically just a constant for an integer. And T is a vehicle type, which is just an enum, so it's basically an integer. So the compiler lets you mix and match those enumerators, but that can lead to bugs. And you need to be really careful about this. You can also use the constant in arithmetic. So you can take a car and multiply it by 5. because the car is basically just an integer constant. With enum classes, that is more strict. Notice when I want to refer to a bus here in this enum class, I need to prefix it with vehicle type. And also if I want to compare now a T, which is a vehicle type, with a color, then the compiler will give me an error. It will tell me you can't compare vehicle types with colors. Doesn't make sense. And also I can't use it in arithmetic because the compiler says, look, this is an enumeration, that's an integer, they don't go together. So there are only advantages in using scoped enumeration, so please prefer those. More sensible example here is we declare an enum class shape type, and there are two variations. One is circle, one is rectangle. Then I declare a struct rectangle. It has two floats inside for width and height. And then I declare a struct shape that contains one data member, which is the shape type. So that's either circle or rectangle. And then I have a union inside that is either a float radius or a rectangle rect. Okay. So how does this look like? How can I use that? I can now create a shape, and I can set its type to shape type circle. Notice I need to write shape type here because it's an enum class. And then I set the radius. And radius is inside a union. Also notice this union has no name here, which is allowed. So here I write to the radius part inside the union, but I can also create a different shape where I set the type to rectangle, and then I write to the rect part of the union. And inside the rect, because rectangle is a struct, I can then write to width and height. And that's one example where I could use a union, but I also store the additional information of which alternative it is. So that's something you might see. Still, like we said before, std variant in C++17 is a better way to do this. But that's like one complete example on how this could look together. Sometimes you want to create aliases. So like there were some questions about like what is size t, what is putterdiff, and I told you those are just aliases to other types. You can create those aliases yourself. And there is like an old way to do this using the typedef specifier. So I can write typedef uint64t and then myint. So myint now is an alias to the type uint64. And the way you can think about this is that if you remove mentally the typedef, it would declare a variable of type uint64. But if you add the typedef, then instead of declaring a variable with that name, it declares a type alias with that name. That's how you can think of typedef. So the same goes for areas. If you remove the typedef in your head, it's an integer variable with 3 elements. If you have the typedef, then pose is an alias to an integer array of size 3. In C++11, we got a better way to do this with using. So I can write using, and then the name of the alias equals the type that I want it to be. So the upper version here and the version down here are equivalent. But it looks nicer if you have arrays and they are more complex type. And one other way, or like one other benefit, is that it supports templates. And we talk about templates at the end of the week. But that's one big advantage. Typedef cannot support templates. OK, so far so good. Any questions to classes and enums? Question?
If you could go one slide back.
Yes.
Looking at line.
Yeah, let's have the mic.
I was just going to ask about line 6 here,
yes,
where you're saying using, so you're redefining this data type, right? Or the name of it.
It's because the line numbers start again here. So like, if I would write that, I get an error because pause is already defined up there. That is true. But if you just think about the lower part in isolation, yes.
So this is, what is happening on 6?
OK, so this declares an alias pose. And pose stands for the type int area of 3. So it's just an alias to the type int area of 3. So if I later write pose p, then p is a variable of type integer area of 3.
OK.
Maybe we can add an example line here.
Yeah. No, it's not a very smart name for a type, right? Pos as a type is meh. You should name the types so that people know what it is. So maybe, if I called it int array, maybe it would be a bit clearer. Using int. Yeah.
Its position. OK. Yeah.
I think my confusion here is where I'm used to whenever I have square brackets and you have a integer there, you're kind of accessing the element in that array.
Yes.
So, but this is, you're defining this as an array with 3. And
yes.
Okay.
So remember back, I guess it was in the morning that then you taught them how
arrays.
to declare an array.
Yeah, yeah.
That would be, you would write int, well, you would really, in the first case, just leave off the type def, and that would create a variable called pos, which would be an array of 3 ints. Mm-hmm. But yeah, especially with type defs, I myself also had to read that line a couple of times to, oh, right, yeah, this is which declares the name and the size of the array.
So the quick answer is if there is a type before, it creates an array, like it creates an array type. And if there's a variable before, then it subscripts the variable.
Cool.
That's the 2 cases.
Okay.
Okay, good. Then let's talk about references. And references are like a pure C++ feature. So like we discussed arrays, pointers, they have already been present in C. References is now a nicer way to refer to something else that is only existing in C++. And you can think of them technically that they are similar to pointers, but they have a couple more guarantees, and they have a bit different syntax. So references can be used as shortcuts to refer to another entity. You can also declare them const. We talk about constness later, but you can declare them const to tell the compiler, look, I refer to a different object, but I will only ever read from this object. And they can be used in function arguments. Let's look at an example. I have an integer I, so that's a variable, and I can now declare an integer reference. And this is denoted by this ampersand. Notice the difference. This ampersand belongs here to the type because I'm declaring a new variable, and this is not taking the reference, taking the address of iref. Because this int here is next to a data type, so I'm declaring here int ref. That is the data type of the variable iref, and then I assign this to I. Notice I don't need an ampersand here, so I'm not taking the address of I like I would do for a pointer variable. I'm just taking I directly, and I bind it to this reference iref. And now iref refers to this variable I. So if I assign to iref the number 3, then the number 3 is written through the reference into the variable I. Also note again, in comparison with pointers, I don't need to dereference this again. So that's the thing about references. I don't need to take the address on the thing they should refer to, and I don't need to dereference them when I want to read through a reference. That's the difference to pointers. When I have a structure, you have a struct A with 2 data members, x and y, and I create an instance of the struct A and call it smaller case a, then I can also refer to the member a.x. So I go to the struct A, the member x, and I bind this to a new reference that is called x. So x is now an integer reference that points into this x inside the struct. And because I declare this reference const here, I tell the compiler I only want to read from this x. So if I write to this x, I will get a compile error because the compiler tells me, look, this variable is const. You cannot write to it. We'll talk about constness more on some later slides. Question?
Wow, nobody has questions on the left.
What's the? Are you basically just using this to say that one variable is just going to be equal to another? Because is that?
So a reference is really just I'm declaring a second name that refers to something else. Yes.
Just as a very quick thing. Let's say you want to create a function that takes the address of some variable that it will then want to modify. In such a case, a reference is an extremely good way of passing the address of, let's say, an integer.
We'll see this in some later slides.
So just inside of, a given code block, naming the same variable many different ways, yeah, that by itself you can do, but you normally wouldn't. It's usually useful when you're then you want to refer to something in a piece of code which does not have direct access to that thing. You want to refer to something in some outside scope.
Yeah, we got to speed up a bit. You need to cut yourself a bit shorter. Sorry about that. But otherwise we won't finish the slide deck. So we'll talk about functions and passing arguments in a bit. So there we will use references again. So maybe that becomes clearer later. I talked about the difference between pointers and references. References allow for this natural syntax. You don't need to dereference anything before. You don't need to take the address of something. References cannot be null pointer. So you also know when you have a reference that it always points to something. It cannot point into nothing. Which also means that when you create a reference to a variable, you need to immediately assign it to an object. You cannot just create a reference and then not point it somewhere or refer it to somewhere. References to temporary objects must be const. So, okay, I'll just leave this. It's a corner case. Pointers can be null because sometimes you actually want that, because you know that you want to refer to something, and sometimes there is no other thing. Like I had the example before where you build a data structure that's composed of chunks, and then maybe in the last chunk you say, okay, I don't point to a follow-up chunk. That's the end of the data structure. So sometimes you want this behavior of pointers that they can be null. And pointers can be declared set to null, and you can let them point to different objects later. So a pointer can change where it points to during its lifetime. A reference is bound once and then always stays assigned to the same object. It's one of the differences. Good practice is that you should prefer references because they have the stronger semantics over pointers, and make them const as often as you can, because that also allows you an easier understanding of your program. If references are const, then you know nobody ever writes through those. It makes it easier to understand a piece of code if most of it is const. Any questions to references? There's a question.
So if I put like a reference as a constant, I can modify the variable, the original variable, and
yes,
and only read from the reference, right?
Yes. So in that example, I have a const int reference, so I cannot write to x directly. But if I would have a.x here, that would be allowed. So I can write via a.x because that is not const. But if I have a const reference, I cannot write through that reference. But through the original object, I can. Yes. Perfect. Question there?
Thank you. About the lifetime, when I would remove a, would the reference x still point or have the value in, or is x?
It's the same as with pointers. If you have a reference to another object and that object dies or goes out of scope, your reference also points into nothing. That's called a dangling reference, and that is a bug. It's an error.
So the reference is always pointing to the a object and not to a memory.
You can never make it point to something else. And because you need to immediately bind that reference to a variable a that was already declared, it's very likely that your reference will live as long because you cannot put the reference anywhere else. But if you had like a function that returned a reference to something inside the function, then you could create a dangling reference this way, for example. So it has the same problems as with pointers. If the thing that the reference refers to dies and the reference still exists, you can have a bug. Question in the very back.
How do you write protect variables within a struct? Is it a similar practice for a class?
If I write what in a struct?
To protect writing to variables within the struct. So we're discussing here, you can't write through a reference, but let's say, you
can put a const here, yeah.
Let's wait until classes, because marking a member variable as const might seem like a good idea at first, but it will just give you headaches.
Yeah. Okay. Then we made references. Okay, let's talk about functions. We mentioned functions a couple times, and functions are entities that also have a name. So here example, I have a function that's called square, and functions now have parameters. So that's a list of types and names that are inputs to those functions. They come in. So like functions in mathematics. And functions also have return types. So in this case, the function returns an integer value. And then inside the function body, which is the part between the curly braces, I can have arbitrary code. In this case here, I just return a value, which is indicated by the return statement. And return means the expression that comes after the return statement, that's the result of the function. That's what goes back to the one who called the function. I can have functions with multiple parameters, like it's shown here, for example. I can also have functions that don't return anything. I denote this by putting void as a return type. And I can also have functions that don't return anything, and they also don't take any arguments. That is also possible. I can make some of those arguments have default values. And I write this by putting, similar as I like define a variable, I put an equal sign and then the initializer in the argument list of the function. So here the function add, it takes 2 arguments, a and b. And if I don't provide an argument for b, then it will be 2 by default. So I can call the function add now with just 1 argument, and the second argument will be 2. Or I can specify both arguments. And then the default 2 here is ignored. I can also set multiple default arguments, and then I could call this even without any arguments, for example. I always need to specify default arguments starting with the last argument. So I cannot put a default value for the first argument, and the caller must specify the rest, because that confuses the compiler which value goes to which argument now. So defaults are always set starting at the last arguments. OK, let's pass some parameters. And there are a couple of what we call, is it a calling convention? It's actually something there. But there are like a couple ways on how I can pass arguments to functions. And by default, if I just define a function, I call it print BS, which stands for big struct and not something else. And I just write the data type here. That passes that thing by value. And that means that the function will receive a full copy of that variable inside its own function. So if I put a variable s of type big struct just here on the global scope, that will occupy a region of storage in memory. And if I now call that function here, print bs with s, then the compiler will create a copy of the data and put it into memory as well. So inside my function print bs, this p here, this will be a separate big struct than the one outside the function. But if I declare the argument to the function as a reference, and then I pass this s, then no copy will be performed. That reference is big struct ref, which is written here with the ampersand. That tells it that this is a reference. That reference will contain the address to the struct s that lives outside the function. So this is a way of how I can give like access to an object into a function. So now inside the function print BSP, I can access the variable q here, and that will directly modify the s that is outside the function, because I refer to that s outside the function. And that's an important difference, pass by value and pass by reference. Here is another example with a small structure that is that just has an integer a that I initialize. Again, notice here the curly braces. I just put a 1 to initialize this int a inside the struct s. Then I call change ss with the small struct s. And notice that I pass it again by copy. There is no reference, no pointer or anything here. So the function change ss receives a copy. So the variable s occupies a piece of memory. There is our 1 here. And if I pass a copy into this function and I assign this p.a to 2, then I will get the 2 inside the copy that is inside my function. And now if that function returns, this means that the scope here ends of the function. Then this inner p, that inner copy, is thrown away. And the variable that lived outside remains with its old state, because the function was only operating on a copy of my data. If I want to have the function change the thing that lives outside, I need to pass it by reference. So here I pass in the reference to the struct S that lives outside. If I now write to q.a inside the function, that writes through the reference q here, and that reference refers to the variable S that lives outside here in our global scope. Because this q is just a reference, it returns it contains the address to that S that lives outside the function. And that allows the function change SS2 here to write and modify the outer object. So if now the function change SS2 returns, that reference variable is gone. But because it was not a full copy and only a reference, the change that happened to the outside variable, it continues to be that way. So the 2 that I wrote to the outer variable S. So S has that state even after the function finished. I have a couple of options. I mentioned pass by value, pass by reference. I could also pass by pointer. And let's discuss a couple of cases here. By default, arguments are always passed by value. So if I don't specify an ampersand or an asterisk for a pointer, everything is copied inside a function. So that is good for small types. If you pass a couple numbers or really small structs, this is fine. If you pass large objects, you should pass them by reference, because a copy, if it's a really big object, it might be expensive. Also, if you want your function to modify the variable outside, you want to pass by reference, for example. If you want to pass your object by reference, because it's a really big thing, but you don't want the function to modify it, you can pass it by const reference. I think I have those examples down here. Yeah, so those are the variations here. If I have a function f that passes a t, which is the struct up here, just by the t, then that will be passed by value. It's a copy. If I have a const t ref, that means I'll pass a reference to my variable a outside here, but the function cannot modify this a because it's a cont reference. I can also pass it by const t pointer. Notice I can also put const on pointers. But this changes the syntax because now I explicitly need to take the address of the outer variable. That would also allow me to pass null here and tell the function, look, I don't have an argument for you. This can sometimes be an advantage, can also be a disadvantage, because f pointer might not actually check whether value is null, and then you would have an error. So usually try to prefer the references as arguments. And if I allow the function fWrite here to actually modify my value, then I can pass it by reference that is not const. And that allows fWrite to change the variable that I have outside. We have an exercise on functions in the afternoon that, that the mentors are going to do with you. Some good practices is also that you should write readable functions, and that means you should keep functions short. Functions should try to do one logical thing. They shouldn't do 7 different things and we have a really bad example later. They should have a good name, so don't call your functions f, g, h1, and whatnot. So like in the example down here, call your function count dileptons if it counts the number of dileptons in apparently some data. And since it returns an integer, it probably returns the count. So that makes it logical what the function does, if it has a good name, if the arguments have good names. Otherwise, you can also document what it does with comments. Also, good example here is somebody printing. Wow. So if your function has like certain subpieces, make those subpieces also functions of themselves. So in your function, you can call another function to do a subtask that your function is supposed to do. So for example, to count the dileptons, we first need to select all the events with muons, then all the ones with electrons, and then we take the size of our d, which is the data. That is a good function. A bad example of a function is you call it run job, but it doesn't say what kind of job it does. Then there is a comment that says, OK, step 1, we do all that. Then step 2, we do all that. The function is really long. It needs those comments because otherwise you would be totally confused on what's going on. So please don't write code like that. Especially if you find yourself writing those header comments, then this is a good indication you want to move that piece into its own function. OK. Any questions to functions? Good. And let's look into operators, which are actually also functions, but functions that have very special names. And operators are functions that use symbols, and I can use them, for example, in between of arguments. Some of those are, for example, plus and minus, which are binary operators. They have a left and the right-hand side argument, and they're pretty logical. Like those perform arithmetic. That's really nice. We've already seen the assignment operator that basically evaluates what's to the right and then puts it into the thing on the left. That's what the assignment operator does. There's also a combined version, which is called a compound assignment. And that is just the shorthand notation for what's written on the right here is like read the variable I, multiply it by 3, and put it back into I. So this is sometimes used as a shorthand if I just want to perform one computation on the same variable, like read it out, do something, put it back. That's the shorthand notation. That can be used with a couple of other operators. And this here is a modulo. So that's the remainder of the division. So if you just put the slash that divides a number by a value, returns the quotient. If you put the percentage sign that divides the number and gives you the remainder of the division. That's sometimes handy. There are increment and decrement operators. So if you just write a variable and then put a plus plus, that just adds 1 to the value. And there are two versions of those. There is the so-called pre-increment and the post-increment, or prefix increment, postfix increment. And they differentiate, like their difference is what kind of value they return. And if you do the pre-increment, it does the increment first, and the result of that expression is the number after the increment. But if you do the increment at the end, then it first gives you back the value that is stored in I and then performs the increment. But this can sometimes be confusing. So maybe try to avoid expressions like that, because then you need to think twice on what's going on. The same works, by the way, with minus minus to decrement a number. So use those wisely.
If I remember correctly, one of the big advertised bugs in recent years had some code like this in it.
Possibly.
Yeah, I sort of remember. Was it one of the OpenSSL bugs, which one of the problematic lines was a very clever line like this,
yeah,
which was not exactly working like.
Yeah. So you can get really clever with those operators, and we see an example in a bit, so please don't overdo this. It can get really confusing very fast. There are bitwise operators which work on the individual bits of a data type. So sometimes you want to work like on the physical representation of an integer in your machine. So there is, for example, the bitwise AND, which just takes the bit pattern on the left, the bit pattern on the right, and it performs for each bit an AND operation. And the result is like the bitwise AND between each of the individual bits. There's also a logical OR. There's a logical exclusive OR, so the XOR operator. Then the tilde just inverts all the bits. It's the logical, it's the binary, the bitwise NOT. And then we are shift operators, which means I take the bit pattern and just move the bits to the left, which is here, the left shift. It just takes the bits and moves it 3 bits to the right, to the left, sorry. And then there's the right shift, which just takes all the bit, and in this case, moves it 2 bits to the right. You don't need to use those very often, but if you work like with hardware devices and you need to set up very specific bit patterns, then you will likely see those at some point. In contrast to the bitwise, which work on the bits, there are logical Boolean operators which work on like the truth values of a data type. So they usually work on Booleans. You can also use them on integers, but they will just regard an integer 0 as false and everything else as true. And they work with only true or false. So I declare 2 Booleans, A and B. If I write ampersand, that is the logical AND. So it will look whether both sides are true, then it evaluates to true. If one of the sides is false or both are false, then it is false. So it's the logical AND. And then the 2 pipes are the logical OR, and then the exclamation mark is the logical NOT. So it turns a true into a false, and it turns a false into true. There are comparison operators. There are 6 of those. there's equals equals, which tells you whether the values left and right are the same, whether they have the same value. There's not equals, and then there's lower equals, then greater and greater equals. And then, as I said before, you can combine those. So that is an expression that uses like probably all operators that you can have. This is actually valid code. So C++ defines the order in which this is evaluated, but not even I know what it does in that sense. So please, please, please don't write anything like that or even have as complex, because it's just the source of bugs and confusion. You can actually go to CPP reference and figure out what it does. So please don't use this. And if you have something that's a bit more complex, maybe use an extra set of parentheses so that it becomes really clear on what is evaluated first. OK, any questions on operators?
Maybe a fun comment that I guess people know that the plus plus in C++ is pretty much coming from the plus plus operator,
yeah,
which C does not have.
So the plus plus in C++, yeah, is actually like means like we take C and we add 1 to it, like we make it the next language. That's where the C++ name actually comes from. Yeah. Nice trivia. Good. And let's talk about control structures. And this is going to be a little longer chapter, but it's quite lightweight. We just talk about the variable ways on which controls can flow through your program and how you can steer control flow. And the first construct we look at is if, which is used to write conditionals, which means that you want to check a condition, and depending on that condition, you want to execute either one piece of the code or another piece of the code. And the way you write this is that you have this keyword if, then you put the condition, and this condition can evaluate either to true or to false. So whatever you compute inside this condition, eventually it needs to be true or false. It needs to be a Boolean value. And if the condition is true, then the statements in this if branch are executed, and those can be arbitrarily many statements. So you can add a lot of code there if you want. And if the condition is false, then the else branch becomes active. And if the else branch contains another if, then this condition will be checked. And if that is true, you go into this if branch. And if the second condition is false, you'll jump again into the else branch, and you start executing here. The else and the else if clauses are optional. So if you just want to check a condition, and if it's true, you only want to perform one piece of code. It's totally enough to just write if condition, open and close curly braces, and like with some code. All that part below is optional. You can repeat as many else if, else if, else if, else if as you want. So you can stack those as many as you need. And if you just have a single statement here, like we have here in the second clause here, so only one statement here, you don't need to put the braces. Some people still would like to put the braces because it formats nicer. It can also avoid some confusion. Like if you ever add a second statement here, suddenly your program would change meaning, because now that second statement would no longer belong into the if. And because this is a source of bugs, some people would like to have the braces always. But that's up for debate. Please ask your colleagues or your project leads on the style they would prefer. Practical example, here I have a function, callout. It takes an integer argument. I check the value of a. If it's smaller or equal to 0, I'll print something and I'll return 0. Otherwise, I check if it's 1, then I return 1. Otherwise, if I divide it by 2 and the remainder is 0, I call callouts with a divided by 2. And if it's none of those cases, that's the else branch, I call it in a different way. So that's the conditional here. There's a second version to write very short conditionals, and that is using the conditional operator. And this works by putting the condition in the front, then writing a question mark, and then what happens if the condition, if test is true, and then what should be returned if test is false. So that allows us to write very concise conditionals, but it can get messy. So I can write, for example, the previous piece of code like that, but now we are in the same situation that I discussed before. This gets really hard to read really quickly. So usually it's preferable that you write out the ifs because they're easier to read. If this conditional is really short, then maybe it's fine if you just use this conditional operator. and avoid nesting them. So here we have the first condition a equals 1. So that's the first conditional operator. Then it gives 1. Otherwise, it calls callouts, and then the argument of the callout is again another conditional operator. So avoid nesting those because it gets complicated really quickly.
I have a question.
Question. Yes.
But we are defining the function callouts, but we are calling the function inside the function. I don't get it.
So this is fine. So you can define a function, and you can call the function itself inside of the function. That is called a recursive call. And that is fine. You just need to be careful that eventually in some version of the function, you return out of the function, don't call the function again, because otherwise you would just infinitely call the function over and over again. And this is done with this with this conditional operator. So if a is 1, then you actually just return 1 from the function and end. But if a is not 1, then you call callouts. So as long as a stays not 1, you recursively call the function itself.
You would get a runtime error because of that eventually.
Yeah.
I ran into that a couple of times. But I wanted to point out.
Is the question answered on Zoom?
Yes, I understand.
Super.
I understand it now.
Perfect. Attila, quick.
Since you were sort of talking more against this exact expression type than for it, I just wanted to point out that the place where you probably want to use it most is not in the return value of something, but usually when you assign a starting value to a variable. This expression is super powerful when you want to say that's a const int equal something. Then you can have a one-liner for const equal int that, well, it could be this if something or that if something. You can, in a one line, declare both that, well, now I made a decision, now it's const, instead of writing int equals 0 if something, then int is rather something.
So it's usable when you declare a variable and immediately initialize it. That's one case where it's quite useful. Yeah, but like try to use it sparingly. Okay, switch statements. Switch statements are similar to if statements, but they usually branch into many, many different cases. And the way you write is that you switch on an identifier, and now this identifier doesn't need to be just a true or false, but it can be any integral value. So that can be a number, for example. And then you list the various cases. And then like if that identifier is C1 or if it's C3, then the code execution just jumps into the case that corresponds to the value of the identifier. One case where this is also useful is for enumerations, for example. You want to switch on an enum value, and then you just list all the enumerators here. And then the code immediately jumps to that enumerator. Then you have as many statements as you like, and then you should put a break statement here. The break statement is not mandatory, but if you don't put it here, and the program jumps to C1, execute statements, and there is no break, it will continue to execute in the next case. That is called a fall through, and it's usually not what you want. So try to always put a break here. You can put a default case, which is executed if none of the case labels was jumped to. So when identifier doesn't match any of the cases, then it goes into the default branch here. And you don't need to put a default branch. Avoid switch statements without breaks. So like with the fall through. It's very confusing, can be a source of bugs. Example here, I have an enum class lang for language, has a couple of enumerators. I switch on language, which is just an instance of this enum lang. And then if that is lang French, I do a piece of code. If it's lang German, I execute a different code. And if it's none of the three, then I just have the default case that outputs I don't speak your language. That would be an example. In C++ 17,
might be worth mentioning, I don't know if you mentioned at the beginning, that the type always has to be either an integer type, a built-in integer type, or something that behaves like an integer.
Yes, it needs to be an integral type, which is integer enumerator. You could also switch on a Boolean, but use an if for that.
But if you want to make a decision on a floating point number, for instance, then use an if, because that's the
Yes, you cannot switch on a float. Yeah. In case you really want to have this fall through behavior, in C++17, compilers are encouraged to warn you if you fall through from one case to the next, so the compiler will give you a warning. And if you really intend to do that, because this is what you want, you can add a fall through attribute at the end of the case statement, and then the compiler will not warn you here. And the compiler will see that this is what you wanted. Okay, so in C++17, we can also put init statements into an if condition. So that's a new syntax. So I put the condition into the second part up there. But before, I get to declare one variable and initialize it, for example. That is useful to limit the scope of this variable. For example, I can declare a variable val. I can get some initialization for that. And then I use that as a condition. And then val is visible in the if and the else branch, but val is no longer visible at the end of the if. So that allows me to like pull one variable into this if I need to set this up for my condition. Don't confuse this with variable declarations as conditions themselves. So this also works. You can sometimes see this with pointers, that people just declare a pointer variable in the if statement and then use the pointer variable itself and let the if test it if the pointer is set or not. Because if the pointer is set, it's a true. If the pointer is null, like it's not set, then that pointer variable is false and you will not go into the if branch. So that's a different thing, but remember those two is like edge cases that you could use the if for. There's a for loop. The for loop has 3 parts in its head, which allows you to initialize a couple of variables. Then there is a condition that's checked before each run of the loop. And then there is a part that is executed after each run through the loop ended, before the next run starts and before the condition is checked. Let's look at an example. That's maybe a more complicated example, but I can declare, for example, 2 integer variables up here, I and j. I set them to 0. Here's the condition inside. The loop runs until I is bigger or equal to 10. So as long as I is smaller than 10, the loop will continue to run. And after each loop iteration, I want to increment I, and I want to set j to I times I. So the way this works is the program comes in from the top. It starts initializing the variables, does the comparison, then executes the loop body here. And then at the end, it will do what is here on the right side, I plus plus, j equals something. Then it will start from the top, check the condition again. If it's still true, execute again. Perform those things at the end, check the condition, run again. That's how the loop runs until the condition is no longer satisfied. If the condition starts to become false, the loop terminates and execution continues after the loop. Don't abuse the for loop syntax. It allows you to declare a lot of things in just one line. It can get really complex fairly easily, so don't overdo it. There's a new type of for loop in C++11 that's called the range for loop, and that simplifies to loop over a range of values. And there are various kind of things that are ranges that we talk about in a different lecture. But for now, you can think about arrays, for example. Here's an example. I have an integer array v. I declare a variable sum, and now I want to loop over this array v. So I can write int a colon, and that means I want to have an integer a in each iteration of the loop. And in each iteration, it should have one of the elements of the range that's on the right side of the column. So because this v has 4 elements, the loop will execute 4 times. And this a will have the values 1 in one iteration, then 2 in the next iteration, and so forth. In range-based for loops, like we had for the if conditionals, we can also put now an initializer there as well. That's allowed in C++20. So that is like the normal range for loop here on the right side. We have an auto here. We'll talk about that in a couple minutes. But I can also declare a variable, for example, here that will just have the scope of the for loop. And that variable will no longer be visible after the for loop. Use this very sparingly. I actually had a hard time to come up with an example where this would make sense. So, but you might see it, that the for loop has two parts, the range for part and an additional variable.
I think that's a pretty good example, that sometimes you want to iterate over a range, but still have an index type variable. That happens.
There's a better thing in C++23 for that, but we don't have it on the slides yet. Okay. There is a while loop as well. That's a simpler one. That just loops as long as the condition is true. So while checks the condition, if it's true, execute statements, check again, execute statement, check again, and so forth. And then there's the do while that just first executes the statement, then checks the condition. If it's true, start again from the top. Statements, check condition, and so forth. If your body is just a single line of code, a single statement, like for the if, you can omit the braces here. But many people like to keep the braces again. Bad example here is I can have a while loop, and because the entire body here is an if, even though it spans two lines, it's one statement, you wouldn't need the braces, but it can be very confusing. Like which part of this is now actually part of the while loop. So please don't do that. There are a couple of control structures inside loops that allow you to jump out of the loop or continue and so forth. Here's an example. I have a loop that just runs as long as 1 is equal to true. 1 is always true, so this loop will run infinitely many times. But inside, I have a check, and if I execute a break inside a loop, that will terminate the loop and execution will continue after the loop. Then in some case, I could hit a continue. Continue means stop running through the loop now and start again with the next loop iteration. We have seen the return already that terminates the entire function, goes out of the function. And then there is a thing called goto that you should avoid, so we don't talk about it. There's an exercise on control structures in the afternoons. Okay, any questions to control structures? Okay, we have 2 more chapters. Those are rather short ones, so I assume we overrun by a few minutes. But we should be fine. Okay, so let's look at headers and interfaces. An interface, when we talk about an interface, we mean a set of declarations so that define like certain functionality, a couple functions, the name of some variables maybe. So if you write like a larger piece of code, you want to extract like the description of the functionality, like the function name, the arguments, the return values, and you want to extract this outside into a separate piece of code that you might want to give to a colleague to show them how your piece of code is like called or used. And you can pull out these declarations in a so-called header file. And the implementation of that functionality can exist somewhere else in a different file. And that is usually the CPP file. And here's an example. I can have a header that just declares the function print hello, has no arguments, returns nothing. And then in a different CPP file, I can include this hello HPP. I can include this header file. So now the compiler knows that this function is available. And inside int main, I can now call this function. And that will compile fine. But the definition, what print hello does, is somewhere else. It's in a different CPP file that is compiled somewhere else separately. That is a very common separation of like just the interface that your code does and the implementation of how it works. And headers usually involve the preprocessor. And this is just a very quick rundown of what the preprocessor can do. We've already seen hash include, which is file inclusion. And include basically does nothing else than read that file and just copy paste that content of the file directly into your source file at the point this include happens. So that will take the content of hello HPP, just paste it here. Then we can define constants with hash define number and then the value. And I can also define what is called a function style macro. So that kind of looks like a function. It has a name, it has arguments, and then it has a replacement text. Notice here that I have this backslash, and that allows the definition of this macro to wrap over into the next line. So I can use this to define multi-line macros. The thing with macros is because they're not proper function, everything is just textual replacement. So the compiler will, if the compiler later sees somewhere my golden number, It will just replace the text with the other text. So this is a much more simple and bare bones version of writing source code. And that has a lot of drawbacks. So whenever you can spell something as a function, please do it. There's also #if that allows you to branch during compilation. For example, if the macro use 64 bits is defined, or when GNU-G is defined, which, for example, is defined by the GCC compiler, then maybe you want to do something else than in the other case. So that allows you to turn like certain pieces of your code off and on. That can sometimes be useful. The good practice here is that you should use this in very restricted cases. For example, to just include headers, or maybe conditionally include. If you compile for Windows, you want to include that header, otherwise you don't. But leave it at that, like only like some platform specifics. Use if and functions and so in C++ for actual code logic. One more thing with headers. If you have a header file, that header file can be included multiple times into your program. One example could be that you have a CPP file, it includes a header, and then it includes a second header that includes the same header again that you had before. So when the compiler pulls in all the includes, suddenly your header would appear twice inside the translation unit that your compiler compiles. And because that can lead to errors, you should guard your headers that if they are included a second time, their content is just erased. And the way you do this is with so-called include guards. So that is not a language feature, but it's a common practice that you say, if not defined, a macro name that should be unique for that one header, then you define that macro, and then you empty-if, and you put your header content inside. So if that header is now a second time in your program, then at the second time, the macro is already defined. And then this if not defined will just omit the entire part of the header. So this way, only the first time the header is included, it will have the content. At the second time, the macro is already defined, and the if just is completely omitted. There's a different way to do this that is called pragma once. This is not standard C++, but it achieves the same behavior. So if you put a pragma once on the top of your header file, and the header file is included a second time, it will be skipped. But it's a not standard C++ feature, but many compilers support it.
Didn't they make it a standard C++ feature?
Not that I know of.
Standards, they did.
Yeah. But you might see it in practice. As I said, many compilers support it. Any questions to headers and interfaces? Or header files? OK. So let's finish up with the last few slides on the auto keyword. And the reason why we have the auto keyword is because very often, and somebody asked that in the mornings, very often it's actually redundant to declare the data type twice inside a statement. So they can be a source of warnings or errors even, and sometimes you actually think that you know the right type, but you're wrong. So for example, you have a std vector, and we see what a std vector is at the end of the week. And if I use the size of a std vector, and that is actually a size t, but maybe I got that wrong, and I just wrote integer over there, then I'm converting a size t into an integer type. And maybe this was a bug, because integer might be a smaller type, so it might not be able to hold the entire size of that vector. So that is one example where it could be a bug. And this is where auto can help us, for example, because auto allows us to omit the data type and just let the compiler figure it out based on the initializer on the right. So if I have a vector of integers here, you can think of that just being an array. So if I use the third element of the array v, then the compiler knows this is an integer, so a must be an integer. I don't need to spell it out, or I could get it wrong here, for example. I just instead let the compiler figure out what the type of a is. The same for v.size. For a std vector, this would be a size t. So I just tell the compiler, look, you figure out what v size is, and you make b that data type. And also make it const, please. So you can combine it with const. It's also useful, for example, in the range 4, when I just want to iterate over all the values in my vector v. I don't care what element type they are, just iterate over those element types. The compiler knows the element type of v, so it can make n the right type. And then I just perform this loop, for example. OK, there will be an exercise to that for the range 4 and the use of the auto keyword. And with that, we're at the end of the course. Are there any questions to loop refs and auto? Or like the auto or the range for? Yes.
I've got a question to the auto keyword.
Yes.
Is it just that it's easier to program, or does it also add some kind of safety?
So auto, okay. So first, there's a lot of controversy around auto because auto, as you said, it's easier to program because I don't need to think what type it is. And sometimes the types can be really complex to spell. So people are inclined to put auto everywhere to make it easier. The problem is, if you later return to that code, let's say 3 months afterwards, or you give the piece of code to your colleague, and the colleague maybe hasn't seen that code before, they can be really, really confused because they have no ideas what types are involved. So using auto in a lot of places can actually make the code much harder to read because there's less information in the source code. It can prevent some troubles where you might get the type wrong. Like we had, for example, with the int up here, even though this should have been a size t, for example, and you used an int here. So that can prevent some bugs, but more oftenly, it can actually make readability harder. So it's a judgment call here, and it takes practice to figure out how to do it best.
Just 2 small comments on this. There's a very few cases, we'll see it with lambdas, where you need it, just because the type doesn't exist, but okay, tiny bit. And the other point is don't trust yourself too much, or at least I don't trust myself at all when coding. So putting the int on line 3, for example, I would be very interested in having the error saying, oh shit, yes, I thought it was an unsigned, it is assigned, or vice versa. And actually, the next thing should change because I was not in the context I thought I was. So from time to time, having some, saying twice the same thing when you discover it's actually not the same or not what you expected is interesting.
And to add to all of this, so auto is sort of a big topic. We just run over it very quickly here, but specifically in Atlas, since you might write code for us, the rule is, we actually have a coding rule for this, that you should only use auto in contexts where it's quite clear what sort of type you're referring to. So when you're creating an iterator, we'll see about iterators later on, sure, use an auto. For size, sure, use an auto. But especially when you're trying to get an element of a vector, which itself might be declared as sort of an auto type, try to avoid that because it makes the code super unreadable later on.
Or another example, you have a function that's called read dataset, and you write auto data equals read dataset. Somebody reads the code. What is a dataset? No idea. If you're not familiar with the code, and then you say dataset.size and then equals auto. Data says at element 2, and that is an auto. And it's like the confusion doesn't stop. So sometimes it makes sense to put in a type there so somebody is not familiar with the code says, it's that type, I can go look there, okay, I understand it. And maybe then the authors later on are okay, yeah. Any more questions to auto? Are there any more questions to the morning lecture itself? Okay.
Oh, I was just thinking out loud here and just kind of trying to think of a situation where auto might actually fail. So I know that in scientific computing, arithmetic overflow type errors are quite common.
Yeah.
And I'm just thinking, could there be a situation if you're, for example, growing an integer and you call it an auto, at first, the compiler first might interpret that as let's say a short, and then you could grow it and then it could fail at runtime? Or are the compilers smart enough to catch something like this?
So when you perform arithmetic with different types on the left and right sides, for example, there are certain rules on what kind of data type will turn out. But sometimes you might have the wrong intuition or you might get that wrong. So if you put an auto on the result variable, the compiler will determine, oh, this obviously goes from shorts to int, and then make the variable an int, and you carry on with an int. Whereas you believe that should actually have been a different type. So sometimes it also makes sense that you write there, I want to have, let's say, a float, because the double is expensive on my architecture, for example, that I want to compute with. So I really want to stick with floats. And if a double starts to emerge somewhere because you had some value times 2 dot, which is a double literal, your compiler would say, oh, the result of this expression is a double. You're putting it into a float, which is a narrowing conversion. Maybe you didn't want that. But if you put an auto here, the compiler will say, sure, result is double. I'll carry on with a double value.
The compiler is smart enough to work backwards from the end result.
No, it's not.
In some cases.
I'm afraid that you might mean that, well, if there is a lot of plus equals statements, then the compiler would figure out that, oh, by the end, you will need an unsigned long. No, it will never do that. The type is chosen where the variable is declared. So in that expression that declares the variable, the compiler will choose a type. If at that point the type that it comes out to be is a short, well, you're stuck with short. That variable will remain a short from there on.
So you can break it in that sense.
Yeah, it's something to be careful. When you're mixing data type, auto can actually make it even more complicated. Yeah. Okay. If there are no more questions, I thank you very much for paying attention and for asking so many really nice questions. There is one more question. We'll see each other in the afternoon exercises. I think the rooms have been assigned. I see a sheet of paper with names on. And so some people will be on Zoom, others will be in person.
I have two more
Question.
items. No, it's not.
Items. Announcement.
So somebody asked where the slides are. Right now, if you go to the Indico event on the main page, at the very bottom, you have a link to the slides. But we'll also attach the version we showed today to the agenda.
Yeah.
And the other thing is, there's a few croissants, etc. left. So on your way out, you paid for it. So pick what you like. And the orange juice as well.
You had one more question? Okay, I can come over.
Can I ask a quick question?
Okay, I'll first take this one.
Because this case is already
There's still the statement.
Because there are very rare cases where it's useful.
Okay.
So one example is that you have a loop that contains a loop that contains a loop.
Yeah.
And in a certain condition, you just want to jump out of the entire loop body. You could use a goto for that case.
Okay, because you can use break, but at the end you
but then
go
you need
into the other one.
But you just go one step outside.
Yeah.
You could also just wrap everything into a function and just return out. That would work similarly. But there are like some very edge cases where you might want to use a goto. Also, goto used to be more liberally used in C for like embedded software. So it might just be nice if like C++ could compile the C code and not fail, just for portability reasons. But you will use it very rarely, if at all. Yeah, but it's supported.
I guess I've used several years ago, like Fortran, and it was
it's also there. Yeah.
But I thought that there was like this debate to erase it from.
Yeah, it's not erased, but you should not use it.
Yeah.
Avoid it.
I know. I remember.
Yeah. Perfect.
Thanks.
You asked me next.
Yeah, can I sign up for hands-on session on a different operation system that is mine?
I don't care. So, I don't know what you filled there. So some of the mentors, they are proficient in various operating systems. So you signed up